All right, so in the last class, we talked about several new concepts. We talked about power. We talked about energy. We calculated the cost of energy. The main thing, we defined the fundamental law of electronics, Ohm's law, and we also talked about Watt's law in our calculation of power. So Ohm's law answered the question, how are voltage, current, and resistance, how are they related? In power, we learned that that was a rate of doing work or a rate of converting energy from one form to another. And then, as I said, we were able to calculate the cost of energy if we know how much each kilowatt hour of energy costs. And so those were the expectations, those were the objectives for the last class. Today, what we want to do is start talking about circuit configurations. There are two basic ways to connect circuits. You can connect circuits in series, you can connect circuits in parallel. So I actually let me show you an example of what I'm talking about. So let's say I have these devices, doesn't really matter what they are, maybe light bulbs. Maybe we got 3 light bulbs. So I got 3 light bulbs, and here's one light bulb, another one, and another one. So I can connect the light bulbs like this, kind of end to end, kind of daisy chain them together. And the way to think about this is, if you think about electricity flowing, current flowing into this connection of light bulbs, that current will go through one bulb, and then another bulb, and then another bulb. Whatever current enters the first bulb, enters all the other bulbs. As a matter of fact, whatever amount of current flows through any bulb is the same everywhere in the circuit. So when there's one path through which current can flow, one path, we call this kind of circuit a series circuit. So we'll look at series connections of devices. If I wanted to, though, I could take these 3 light bulbs and I can connect them like this. I can take a wire, connect the top of each bulb together. I can take a wire and connect the bottom of each bulb together. And now I can think about current flow into this circuit. Current can flow into this wire. Once it gets to that first light bulb, then the current's going to start to split up. Some's going to go this way, some will go that way, it'll split again, and on the bottom it'll recombine and flow back out of the circuit. So here, in this circuit, we have many paths through which current can flow. And the thing about this circuit is, whatever voltage I have across here, say if I put a battery here to power this, that voltage is the same all the way across the circuit. So when you have a circuit where there's many paths for current to flow, but one voltage across the whole circuit, we call that type of circuit a parallel connection or parallel circuit. So these two connections, these are the two basic connections, two basic ways you can connect up devices. You can connect them in series, you can connect them in parallel. So what we want to do, at least this week, we want to learn about connecting stuff up in series. How do resistors behave when you connect them up in series? How do voltage sources, batteries behave when you connect them up in series? So today, we'll look at series connection of devices. And then next week, we'll look at parallel connection of devices. We'll look at how these devices behave when you hook them up in parallel. And the idea is to get really, really good at doing series calculations and get really, really good at doing parallel calculations, because ultimately what we want to do is combine these two. So I can take one bulb like this, maybe I can take one like this, and maybe 2 like this. If I connect the top of these together and the bottom of these together, then these two are in parallel. But this one right here, if I connect it to the parallel connection of light bulbs, this one is in series with the parallel combination of the 2 lights. This is what we call a series parallel connection. It's a combination of the 2, series, parallel. And so here's where things start to get a little bit more complicated, because we can put together some pretty interesting series parallel circuits. And if you're good at your series analysis, if you're good at your parallel analysis, then in theory, when you put the two together, the learning curve to solve a circuit where there's many types of connections, series parallel connections, it shouldn't be too bad. So today we want to focus on series circuits. I want to look at how resistors behave when you hook them up in series, and I want to look at how voltage sources behave when you hook them up in series. And in addition to that, there's another assignment that's going to count as a quiz grade. I think I gave you a couple already. You had a universe assignment. You did watch the video, and you wrote a small paper for me that counted as a quiz grade. There was a supplementary quiz that you guys did. You would have turned that in today had we met today. And so here's another one. There's an energy project that would have been turned in today. That counts as the quiz grade. And now I'll give you a battery assignment. This battery assignment I'll talk about a little bit later on, but that also will count as a quiz grade. So I'll have a little bit more to say about that a little bit later. So let's get started with the class. Let me I don't know if you had a chance to download the document for today, but let me just quickly if you can, go ahead and download the topic sheet at least. But I'm going to display it just for a second, and you can get an idea what we want to do. So we want to talk about the series circuit, resistors in series. How does current behave in the series circuit? How does voltage behave in the series circuit? We're going to learn the difference between a voltage source and a voltage drop. Those are two terms that you'll get to know about today. A voltage source, we've already talked about voltage sources, but a voltage drop is something new. We will apply Ohm's law to circuits, to series circuits, and see how to apply Ohm's law, and we'll use actually Ohm's law and Watt's law together to solve the circuits. And then we'll introduce our first of two laws we're going to learn about this semester. Kirchhoff's voltage law. There's a rule called the voltage divider rule, so we'll talk about what a voltage divider is, and I'll introduce the voltage divider rule to you. And then finally, we'll see how power behaves in the series circuit. So that's the goal today. So let's start by just kind of looking at a connection of resistors, and I'm going to connect those resistors up in a way that we call a series connection. And I want you to think about something as I connect these up on the board. So if you remember, the way you draw a resistor is draw it it's like the bottom of a saw. And so I have this resistor, and I want to add another resistor to it. I'm going to do this. Now I can call this resistor R and this resistor R, but typically what we do is we subscript the resistor if they're two different resistors. So these two resistors don't have the same value. I want to explicitly show they don't have the same value. I'll call this one R1, R2. If I wanted to, I can keep putting these in series. I can keep putting them in series. I can keep drawing them, but what we do is you may have seen this in math where they'll have three dots. So I'll put a dot here, and the dot here. Does anybody know what those three dots mean? Have you ever seen that before in math or maybe in another science course? What do they mean?
It just keeps going on and on.
Yeah, it keeps going on and on, just like these two. So these three dots, whatever I'm doing on the left, you just keep going on and on and on. So I will keep putting resistors in series. I just keep drawing them. You don't want to do that. These dots is a shorthand way of showing I want to keep adding resistors together just like this. And when you want to stop, you go over to the last one, draw one more, and then this is R1, R2, this will be R1, 2, 3, 4, 5, 6, 7, however many you have, but the very last one you call that Rn. And that's kind of a shorthand way. So let's say I have a circuit in series and I have 75 resistors. Well, I don't want to draw all 75 in series. If they're in series, I can draw the first two in series, so you can look over here to see how they're connected. Dot, dot, dot means they continue, and then this last one, that N, would have a value of 75, and then I can just look at the circuit, and I can say, hey, there's 75 resistors connected up in series. I don't know what the values are of the ones that I'm not showing, but I do know there's 75 resistors. in series. And here we're going to keep it general. We're just going to call this N. Now, let's say you're looking through here. This is your eyeball. You're looking into that resistor. Let's say you can see inside that resistor. And let me just change what I did before. Now, if I want to show the resistors have the same value, what I can do is I can erase the subscripts. So I'm going to show this down here. Say I have one resistor has a value of R, whatever that is, R. And you're looking at that. Well, actually, let's think of it this way. Let's think of current flowing into that resistor, R. Now, what does a resistor do? Well, of course, we said resistance is the opposition to current flow. So what a resistor does is it adds opposition into a circuit. And so this current now is feeling an opposition or a pushback of however many ohms R is, R ohms. But the point I want to make is this current is feeling a certain amount of opposition. If I add another resistor that has exactly the same ohmic value as the first, now that current is going to feel twice the opposition. And in that case, less current is going to get through because it's twice as hard for current to get through. If I add another resistor, exactly the same value, R, now that current is going to feel 3 times the opposition. And the point is, I can keep on adding resistors and adding resistors and adding resistor. And if I keep adding resistors, what happens is it gets harder and harder for current to flow through the circuit. So less current flows through. And in theory, I can add so many resistors in series, it becomes so difficult for current to flow through that all the current stops. The point I'm making is this, is that as you keep adding resistors in series, the total resistance goes up, and the way it goes up is you sum the resistors. So how do I say that mathematically? Well, look at this picture, and I can develop a formula from the picture. The total resistance, the whole resistance, I'm going to call that RT, R, I'm going to subscript that with the T, and it should make sense to you. You should have the kind of a gut feeling. It has to make sense that the more of these I put in, the way of the current, the harder it is for current to go through. I kind of call this the grocery cart problem. And I don't know if I do a good job explaining this. When you're face to face, the students get it. But remember, you go to Kroger's or Sam's or wherever you shop for groceries, the kid goes out to get the grocery carts, and he starts off with one grocery cart, and he pushes it, and he gets another. The grocery carts are like the resistors. He starts off with one grocery cart, then he puts another one in front of that. It's a little harder to push, but he or she can still push it. Then he gets another one, and another one, and another one. And before you know it, that person has a whole row of grocery carts he's trying to push, but it's really hard for them to push. In theory, you can have so many grocery carts to the line of grocery carts that it's impossible for the kid to push it. That's the back push, the resistance I'm referring to. So this acts the same way. And mathematically, the total resistance would equal the first resistor plus the second resistor, plus the third resistor, plus the fourth resistor, plus however many resistors you have. I just add them all up. And I don't want to have to draw a bunch of resistors. So again, I just show these 3 dots. So it's this one, plus, and remember the 3 dots, what that means is whatever you were doing over here, you keep doing it. And here we were adding, so you're going to keep adding, R3, R4, R5, until you get to the last resistor. Then you'll take that last one and you'll add that up too. And so this is the first formula that we have for a circuit that has more than one resistor in it, the series circuit. And what this says is that in the series circuit, the total resistance is additive. You want to write that down. Write the formula down. And the words I'm saying is, in a series circuit, the total resistance is additive. The more resistors you add, the more total resistance you get. So here's the first formula. If you're keeping the formula sheet separately, this is a good one to write down. If you keep adding resistors in series, the total resistance goes up. Now, if that makes sense, hopefully it does to you guys, I need to pause for a second and describe something to you. And if it's not clear what I'm saying, then please stop me and ask. I need to talk about the difference between a voltage source and a voltage drop. So let me talk about that for a second, then we'll come back to this circuit. So, and actually I can probably do it right here. So a voltage source. And that's a really simple one to talk about, because a voltage source is anything that creates voltage. A voltage source is anything that creates voltage. Well, what kind of things create voltage? Batteries create voltage. Generators create voltage. Solar cells create voltage. Well, what do you mean by create voltage? Well, what is voltage? We learned the second week of class that in order to create voltage or an electrical potential difference, all I have to do is what? What is voltage?
Electromagnet or electromotive force.
It is an electromotive force, but how do I get that electromotive force? What do I need to do, or what does a battery need to do?
Separation of charge.
Separate charge. A voltage is nothing more than the separation of charge. And the way the electromotive force comes in is once you separate charge, between the two regions of charge, there's an electric field. We talked about this. You separate charge. If I separate masses, I have a gravitational potential difference between this point and this point. But instead of masses, if I separate charge, I have an electrical potential difference between this point and this point. If I separate masses, what's between the two masses is a gravity field. If I separate charge, what's between the two charges is an electric field. And once you put an electron in the electric field, it's going to experience a force. It's going to want to move to the positive. And that force is called electromotive force. So we learned about all the physics behind that. So a voltage source is anything that separates charge. Batteries separate charge. Generators separate charge. Solar device, solar cells separate charge. And you know the symbol. We talked about the symbols already. One symbol for a voltage source is like this. One is like this. Now today you'll learn the difference between these two. There's actually a difference between this and this. What I said was I think it was last week, I said you can use any of these as if they were the same, but strictly speaking, these two are different, and you'll learn about the difference today. And then the third way to draw a voltage source is like this. So I gave you several ways to draw a voltage source, and a voltage source is anything that creates a voltage. Okay, so that's pretty simple to talk about, but the one that you got to think about, the new term is voltage drop. So let's talk about voltage drop. So the voltage drop. So what is a voltage drop? A voltage drop is what you get when current flows through a resistor. A voltage drop is what you get when current flows through a resistor. This equation, Ohm's law, says that voltage equals current times resistance. And so if I have a current flow through a resistance, I get a voltage. And the voltage that exists across that resistor is called a voltage drop. Voltage is actually drop. And so the thing about voltage drops is a voltage drop, you can only have a voltage drop. You got to have two things. You got to have resistance and you got to have a current flowing through that resistance. If you take away either one, you don't have a voltage drop. So if I have 0 here for resistance, I don't care what my current is, my voltage drop across that resistor will be 0. I don't have a resistor because it's 0 ohms. But if I have a resistor, but that resistor has no current flowing through it, then again my voltage drop is 0. So voltage drop is what happens when current flows through a resistor. When current flows through a resistor, if you take your voltmeter and put it across it, you'll read a voltage across that resistor as long as current is flowing through it. If you stop the current, the voltage drop goes away. That's not true with a voltage source. A voltage source can either have current or not have current. It'll stay the same. So what I'm saying is, let's say I have a battery, a car battery, so it's 12 volts. If I don't have anything connected to that battery, there's no current flowing. And then there's no current flowing, but yet I can still take my voltmeter that you guys will use, your multimeter, and I can connect it up across that battery from here to here, and it's going to read 12 volts. If I connect it across 12 volts, it's going to read 12 volts. But there's no current flowing. So there's an example of a voltage source producing a voltage and there's no current. Or if I wanted to, I can connect up something over here like a light bulb. I can connect up a light bulb, and now the light bulb is going to light up, but that voltmeter is still going to read 12 volts. It doesn't care whether current is flowing in the circuit or not. So a voltage source will read a voltage if there's current or if there's no current. It doesn't matter. A voltage source will always read voltage, regardless of whether the current is flowing in the circuit or not. A voltage drop is produced by current, so if I don't have a current, I do not have a voltage drop. Okay, so remember, associate voltage drops with resistors. Let me show you one more thing about voltage drops. Let's say I have that same 12-volt battery. And I take two resistors. It really doesn't matter what value they are, but all I know is they're the same value. I take two equal value resistors, I connect them in series, and connect them up to the battery. If these are the same value resistors, then each one will drop voltage. And if they're the same value, this is going to get half the voltage, and this is going to get half the voltage. So I have 6 volts across this one, and now I have 6 volts across that one. They'll get equal voltage. So each one drops 6 volts. The total's got to add up to 12. If I have 3 of those resistors in series and they're all equal value, then each one's going to drop 4 volts. If I have, say I don't know what the values are, but I know that this one right here is twice. I know that this one is twice the resistance of that one, and that one's going to have twice the voltage drop of that one. So the point I'm making is resistors drop voltage, and that happens when current flows through them. Now, if I take my voltmeter and put here, I'll read 12 volts. If I take my voltmeter and I put right here, if these two are the same, I'm going to read 6 volts. But if I come up here and I open it up so current can't flow, and that voltage was reading 6 volts, it's going to go to 0. Why does it go to 0? Because in order to have a voltage drop across a resistor, I got to have a current flowing through it. And if you open up the circuit and stop the current, then that voltage drop, the current is 0, so that voltage drop will be 0. So I'll say it one more time. A voltage source will be one of those figures I drew. Battery symbols. It's anything that separates charge to create a potential difference to create a voltage. A voltage drop is what happens when current flows through a resistor. And that voltage drop is defined by Ohm's law. The voltage across the resistor is equal to the current through it times the value of the resistor. Now, having shown you that, what I want to do now is our resistors that we hook up in series, and we kind of derive this equation from it. I want to hook up a battery to this and let current flow through it. Let's see what happens. So what I'm going to do is hook up a battery. To this. And now the battery hooked up, current can now flow in the circuit. And so what's going to happen is current is going to flow out of the battery through this resistor, through this resistor. That current is going to flow through all these resistors. And what happens when current flows through a resistor, if I have a resistor and current flows through that resistor, what I get is a voltage drop across the resistor. So when that current hits all these resistors, I'll get a voltage drop. And typically what we do is we name the voltage drop after the resistor. So for what I'm saying is, if this is R1, the voltage drop across R1, I call that V1. V1. This is R2, the voltage drop across that resistor, I call that V2. We name the voltage drop after the resistor that's causing the voltage drop. And so you can see that for every resistor I have, current, that same current is going to flow through it, and so there's going to be a bunch of voltage drops. And what I can do to this equation that we derived, this is for resistance in the series circuit. I can actually play around with this equation. And let's say I multiply this side by current. So I multiply the left side of this equation by current. And you know in math, I'm allowed to do that so long as I do the same thing to both sides. So if I multiply the left side by current, I got to multiply the right side by current. Now, if I put the current over here like that, is that multiplying the right side by current? Did I do that right? Is my math correct?
No, it has to be applied to every resistor, not just one on the end.
Exactly. So what he's saying is, no, your math is wrong. Say no thing. If you show it that way, what you're saying is take Rn and multiply by I. But what we said was, in order for this to be a valid algebraic equation, whatever I do to one side, I got to do to the other side. So I can't multiply that one term by I. I got to multiply that whole side by I. And the way you indicate that is by using parentheses. What I really want to say is, I want to put this in parentheses. And now I maintain the equality. Well, remember what I said about you name the voltage drop or the voltage after the resistor? Well, this resistor is called RT. So if I take, anytime you take I times R, you get V. Ohm's law says if you take I times R, you get V. But which V? Is it a voltage drop or a voltage source? Well, if I take the current times the total resistance, what I get over here is the total voltage. That's this. That's the total voltage. It's the battery voltage. And it's saying that that's equal to, then I got to take into account, I got to multiply every term in the parentheses by this current. So when I multiply this I times that R1, I get a voltage drop I'm going to call V1. And I'll do this times R2, I get a voltage drop, V2. Plus, and I'll multiply this time all those resistors in the middle that we're not showing. So I'll show that down here with 3 dots. All the way to the last one, when I multiply that current times that last term, I get Vn. And now by taking that resistance equation we started with, and by multiplying both sides of it by current, we get this new thing. We get this new relationship. It says that the total voltage is equal to the sum of the voltage drops. The total voltage is equal to the sum of the voltage drops. And this is a very, very important relationship. It's called Kirchhoff's voltage law. Now, I'm not going to spell Kirchhoff. It's on the topic sheet. You can look it up. But it's called Kirchhoff's voltage law, and we usually abbreviate it KVL. Now, depending on whose YouTube video you look at, some people pronounce it Kirchhoff, some people pronounce it Kirchhoff. I don't know which it is. The guy was German, and the Germans have really hard syllables. So it's probably Kirchhoff, like you're coughing. I don't know. But the point is, this is important. This is the first of 2 laws we'll learn. 2 new laws. And this is called Kirchhoff's voltage law, and we abbreviate this KVL, Kirchhoff's voltage law. So sometimes you'll solve circuits, and they'll tell you to prove KVL, and all they want you to do is add up the voltage drops to make sure they add up to the total voltage. So yeah, that's a really simple formula right there, but it has a lot of uses. For example, if you understand that, then if I give you a circuit like this, if I have a voltage source that's 5 volts, and I tell you that I have 2 resistors, and I tell you the voltage drop across that top resistor There's 3 volts. What's the voltage drop across that resistor? How much is it?
2 volt.
Gotta be 2 volts. Why? Because Kirchhoff's voltage law says the sum of the voltage drops gotta add up to the total voltage. So if this is 5 volts across both resistors, you're telling me that there's 3 volts across that top resistor, then that one's gotta drop 2. So Kirchhoff's voltage law is really, really simple, but we use that throughout all of this semester. You'll use that throughout all of next semester. Matter of fact, if your major is one of the electrical majors, you'll never get rid of Kirchhoff's voltage law. Probably second to Ohm's law. It's the Kirchhoff's voltage. He actually has 2 laws, but we're talking about the voltage law. Very, very, very important law. Okay? So, what have we learned so far about resistors in series? Well, we learned that if I keep adding up resistors in series, the total resistance goes up. So think about that formula was RT was R1 was R2 plus all the way out the Rn. So that was our first formula. And that says that the total resistance in a series circuit is additive. Total resistance in a series circuit is additive, which means if I keep adding resistors in series, the total resistance goes up. Now, if you wanted to, you can put that in Ohm's law. We learned about Ohm's law last week. It says the current equals voltage over resistance. And if this is the total resistance, that resistance, and I keep adding resistors up in series, then that means that this part of this equation is going up. If I keep adding resistors in series, the total resistance is going up. What's going to happen to the current?
It's gonna drop.
It's going to go down. Now, I don't know if this was the class or it was my day class, but I mentioned something that was kind of profound but kind of simple. And what I said was, in electronics, all we do is control current. Your cell phone, as complicated as it is, all the stuff it does, all you're really doing in there is manipulating current. And there's basically 2 ways you can control current. You can control current by changing voltage, or you can control current by varying the resistance. Either way, you'll get what you want. Usually, though, we don't change the voltage because the voltage is usually fixed. Voltage is usually fixed. When you plug something into the wall, it's 120 volts. You can't change that. It's fixed. When you go get a battery and put it in your device, let's say you got a AA battery, it's 1.5 volts. It's fixed. You don't, typically voltage is fixed. So the only other thing left to vary, if I want to control current, is some kind of way to change resistance. Now, if we would have had lab today, we would have spent a lot of time talking about this. And I would have shown you a very, very, well, actually 2 very, very special resistors that we use specifically to control voltage or current. But because I wasn't really sure what the weather situation was going to be, I figured by later on in the day, it probably would be okay. I had to cancel the morning classes. So I woke up this morning, it was, about 9 inches of snow, and I live on a hill taking care of my mom. And I can get down the hill, but I can't get back up. I don't have 4-wheel drive, so I figured it'd just be safer if we stayed home, and then maybe next week we can do our face-to-face and we'll get into this. But this is actually quite important, this varying resistance, and I think when I show you that in lab, you'll be pretty impressed by what you can do just with that simple equation. So the resistance formula. And then there's this one that says that in a series circuit, if I have current flowing through resistors, then each resistor is going to develop a voltage drop. And I learned from just multiplying both sides of that equation by current that the sum of those voltage drops has got to equal the total voltage. And so we wrote that like this. We said that total voltage is going to equal V1 plus V2 plus however many resistors I have, the voltage drop across all of those, out to that last resistor, Vn, and those voltage drops has got to add up to the total voltage. And so that one has a name, this guy named Kirchhoff. Observed this to be true, and so they call this Kirchhoff's voltage law. They name it. They don't have a name for that one, but that one's actually the name, Kirchhoff's voltage law. And then What about power? What about power in the series circuit? I can just look at this circuit and I can observe a couple things. Number one, I can see that the way I have this drawn, there's only one path for current to flow. In a series circuit, that's the very definition of a series circuit, one path for current. So since there's one path for current, that means the current is the same everywhere in the circuit. So let's say that there was 5 amps of current on in that circuit, and you wanted to measure it with your meter. And I'll show you how to do that. When you guys come in, you'll bring your digital multimeter. We'll measure voltage, we'll measure current, we'll measure resistance. You'll learn how to do that. But if you were actually measuring the current here, it wouldn't matter where you put your meter. You can put it here, here, you can put it anywhere, because if 5 amps of current leaves the battery, that same 5 amps has to flow through R1, that same 5 amps has to flow through R2. Matter of fact, that same 5 amps has to flow through all the resistors to get back to the battery, which means that in a series circuit, the current is the same everywhere. And so we observe, number one, in a series circuit, the resistance is additive. You keep adding resistance, the total resistance is going to go up. Here, every time I have current flowing through a resistor, it creates a voltage drop. We learned that the sum of those voltage drops has got to add up to the total voltage. That's so important, it gets its own name, Kirchhoff's voltage law. And we learned that in the series circuit, there's one path through which current can flow. Another way of saying that is that in a series circuit, the value of the current is the same everywhere. In the series circuit, the value of the current is the same everywhere. And so the final thing I want to talk about is power. How does power behave in a series circuit? And it turns out that that's the simplest of all, because power, no matter what kind of circuit you have, series, parallel, or a combination of the two, power is always additive. Power is always additive. So if you go back to the example I gave you at the beginning of class, I had 3 light bulbs. I had 3 light bulbs like this. I have 3 light bulbs like this. And I have 3 light bulbs like this. I had a series circuit, I had a parallel circuit, and I had a series parallel circuit. Let's say that the wattage of the light bulb is 10 watts. This is 10 watts. This is 10 watts. This is 10 watts. If I say, all right, what's the total power dissipation of that series circuit? You add them up. The total power dissipation is 30 watts. Down here, if this is 10 watts, this is 10 watts, this is 10 watts. Now they're hooked in parallel. So hooked in parallel, things will change, but what will not change is the total power. Total power is always additive regardless of the circuit. I still got 10 plus 10 plus 10, 30 watts. And over here, where I have a combination of the two, if this is 10 watts, this is 10 watts, and this is 10 watts. Again, if I want to find the total power dissipation, I just add them up. I got 30 watts. The reason for that is, remember what power is. Power, one definition of power is energy converted per unit time. So think of power as just energy in motion. That's all it is. And energy is conserved. The conservation of energy principle says energy cannot be created or destroyed. You can only change it from one form to another. And so I don't care how the energy is being delivered, in series, parallel, or a combination of the two. If I have a certain number of joules per second, it's going to be the same in the whole circuit regardless of how it's connected. So it's independent. Power is independent of the connection. Power is always additive. So how do you write that mathematically? Well, that's pretty simple. You do it this way. You say that the total power in the circuit is equal to the power dissipation of the first resistor plus the power dissipation of the second resistor plus all the way out to the power dissipation of the last resistor. Now I'm using the term power dissipation. You'll see that as you read the book. He'll say how much power is being dissipated by this resistor. And that word power dissipation or power dissipated, what they mean is, think of we talked about in the last class, transducers. A transducer is any device that changes energy from one form to another. A transducer from last class is any device that changes energy from one form to another. Well, a resistor is a transducer. A resistor changes electrical energy to heat energy. And the process of changing electricity to heat, we call that power dissipation. And so you'll see that term, dissipation. But here you go, you got your three formulas here that we came up with. This applies to series circuits. This applies to series circuits. And this applies to any circuit, regardless of how they're connected. And so now we have a toolbox. We got these mathematical tools in our toolbox. We got these, which are specific to series circuits. And then we got what we learned about last week, which we learned about Ohm's law and three ways to write it. We know that I is V on R, V is I times R, and R is V on I. So we talked about that. And then we talked about Watt's law, which says that power is voltage times current, and we substituted for V and I using Ohm's law in combination with Watt's law. We came up with P equals I squared R, and P equals V squared over R. So we got these set of equations that apply to a series circuit, and then we got these over here that we use in conjunction with those to help us to solve whatever kind of circuit we're trying to solve. And the only thing to remember about a series circuit, the current in a series circuit is the same everywhere. So with this set of equations and understanding that the current is the same everywhere in the series circuit, in theory, you should be able to solve any kind of series circuit. So what I want to do is I want to practice that. I want to practice solving series circuits. So that's what we're going to do next. Now, as we do that, I want you to remember what I said in the last class. What we're going to do in this class is we're going to give you problems, and they'll be stated as word problems, and you got to be able to translate the word problem to an electrical diagram called a schematic. I want you guys to get used to drawing schematics, because what's going to happen is these schematics, as we go on through the semester, are going to get more and more and more complicated. You just can't jump right into a complicated schematic. You got to kind of build your way up. So I'm going to give you some practice problems here in just a minute. What you'll do is you'll read the problem. Read it. If you got to read it more than once, that's fine. Read the problem and read it as many times as you need to read it to understand it. Once you understand what you're being asked, I want you to model the problem. Draw a picture based on the schematic symbols I introduced to you in the last class. So draw what you think that might look like. And if you don't know, just do the best you can. As we go through the semester, you'll learn how to draw it correctly. So read, understand the problem, model the problem using an electrical schematic, the symbols that we talked about in the previous class. Write down what you know, the values you know on your schematic, write down what you're looking for, and then you got all these tools to help you find what you're looking for. But remember, in a series circuit, the current is the same everywhere. So one rule of thumb you might apply to this is when you're trying to solve a series circuit, if you find current, then you find a value that you can use everywhere in the circuit. So sometimes it pays to find current. It just depends on what you're doing. So I want to give you some practice problems before I do that. Let me pause to see if anybody has any questions over anything I talked about here so far regarding series circuits. Any questions or comments? All right, well, if there are no questions or comments, then I want you to get a sheet of paper. You might need a couple sheets of paper. You'll need a calculator, and one of the things you guys need for the class are two things. You got to have a straight edge. I recommend either 6 or 12-inch ruler. I recommend a clear ruler. It doesn't have to be clear, but now you see, we're going to draw these schematics. This you can just sketch by hand. I don't care, but if there's something you turn in for me, it needs to be neatly done. Drawn with the ruler, straight edge, so I can look at your picture and understand it. So if you get a clear one, if you lay the ruler on top of your diagram, you can see under it. So that's kind of helpful. But what you'll need is a straight edge, some kind of ruler. You'll need a set of coloring pencils, and And as we go through the course, you'll see me color coding more and more things. I'll use one color for current. I'll use another color for voltage drops. I'll use another color for power dissipation. Because what's going to end up happening in a couple of weeks, this whole board will be filled up with stuff, and it'll drive you crazy trying to keep it straight. If you color code it, it's much easier to solve the circuit. So what you need is paper right now, calculator, your coloring pens or pencils, and a straight edge. And what I want you to do is look at these problems, the first couple practice problems on this page, and see if you can solve them. So I want to look at the first three. Problem number 1, 2, and 3. See what you can do with those. And remember, do not just draw or do not just write the equation and solve it, even if it's easy to do that. Draw the picture first, define all the elements in the pictures, and then use that picture to solve the problem. So I'll be quiet for a while, let you guys work on the first 3 problems, and then I'll come back and we'll take a look at those together, and then we'll take a little break. See what you can do with problem number 1, 2, and 3. Guys, I'm gonna give you about one more minute, and then I'm gonna look at that first problem. I'll give you a few more minutes on the other ones, but I'm gonna look at the first one in 1 minute. All right, I want to look at the first problem. Problem number 1. A 9-volt radio requires 200 milliamps to operate. In order to operate the radio from a 12-volt battery, what size resistor must be connected in series with it? So what you want to do, you want to read this problem as many times as it takes you to understand what they're asking. We have a 9-volt radio, requires 200 milliamps of current to operate. In order to operate the current from a 12-volt battery, what size resistor must be connected in series with it? Now here's what I have when I read that problem. I have a 12-volt battery, that's one thing I have, and I have a radio. Now remember what we said, I showed you how to draw the schematic for a voltage source, the symbols for voltage source, current, and resistance. If it's something you don't know, you just make a box and you can label it, or you can show it as a resistor. I chose to, I don't know how to draw, I don't know what the graphic symbol is for a radio. I just drew a box and I call it radio. Now when I have something like this, it's a 9-volt radio, which means you're supposed to hook up a 9-volt battery in order to get the thing to operate. You don't have a 9-volt battery. All you have is a 12-volt battery. So some kind of way you got to reduce the voltage down. You got to drop the voltage down to the proper level of 9. But what do we use to drop voltage? Resistors drop voltage. Now this 9 volts, and the way I have it, what I like to do when I'm drawing a schematic, and this is just something that I do, I'll use a certain color for the voltage drops. I'm using orange for voltage drops, and this, I'll draw a circle around it, and that represents a voltmeter. So you guys will see me doing this, and I want you to know what I'm doing. You'll see me draw a voltage over here, not a source voltage, but a voltage drop. I'll draw it, but this actually represents a meter. So this represents the leads of the voltmeter. You got your positive and negative lead that connects here, and it connects here. And what I'm showing on that meter is that if you connect across the radio, then that meter is going to read 9 volts if it's operating. Don't confuse this. Don't think that this is part of the circuit. It isn't. The circuit is just the radio, the battery, and the resistor. This is not part of the circuit. I'm just indicating what the value is. Now, let me ask you a question though. The way that the problem is written, it says we have a 9-volt radio, requires 9 volts, and all we have is a 12-volt battery. Why can't I just do this? Why can't I just, since this is more than that, why can't I just hook this directly up like this? Why can't I do that? What's wrong with that?
The voltage are not equal.
The voltage is not equal. That is correct. And what do you think is going to happen if I take something that requires 9 volts and I put more voltage across it than it's designed to handle? What do you think is going to happen to it? Somebody said it's going to fry it. I like that. It's going to burn up. Typically, that's what happens. And what causes it to burn up? Well, it says in the problem statement that the current draw is 200 milliamps. What determines the current something takes is the resistance of the device. So that 200 milliamps is 200 milliamps because you took the voltage across the radio, the 9 volts, divided by the resistance of the radio. We don't know what that is. Inside that radio, there's resistance. But if you take the 9 volts of the radio that require to operate the radio, and the resistance of the radio, that's V over R, that's Ohm's law, that gives us current. That's where that 200 came from. So this radio needs 200 milliamps of current to operate. If you go above that, you'll send so much current through it that you burn it up, you fry it. If I change this, if I raise this up from 9 to 12, which will happen if I connect this directly to the radio, then you're also going to raise this current up. So instead of 200 milliamps going into it, you'll have a higher current. We don't know what it is because we don't know the resistance of the radio, although we could find the resistance of the radio pretty easy. But that's not what the problem wants. The point is you can't do that. You can't say to yourself, well, I only need 9, I got 12, let me connect that baby right up and get it to work. It may work for a minute, but you're going to fry it. So you don't want to do that. What you want to do is some kind of way reduce this voltage down to a level, a safe level that the radio can handle. In this case, we need to drop the voltage from 12 volts to 9 volts. And the way you do that is by placing a resistor in series with the radio. So I got this resistor in series. Now, does it matter where the resistor is? No, it doesn't. The order of it, you can tell that if I have the total resistance equals R1 plus R2, the total resistance also equals R2 plus R1. If I look at Kirchhoff's voltage law, the voltage in the circuit is going to be V1 plus V2, or I can switch it around. The order of these doesn't matter. So you don't say to yourself, well, the current's going to hit, as soon as I improperly think, well, current's going to hit this resistor first. And don't think like that. Order doesn't matter. Whatever the mathematical law says, the fact that I can add in any order, you can kind of translate that over to the physics of what we're doing. So that's what I got to do. I got to put the resistor here. And that resistor is going to drop voltage. It's basically going to drop from 12 volts down to 9. But the question is, what size does that resistor need to be? What size? And I want to talk about what I mean by size, but I want to hear some answers from you guys. So what do I need to do here? Anybody get an answer for me?
I put a 15 ohm resistor in there.
Yes,
Okay. 15 ohms, and somebody else said that's it. Who said that? Put a 15 ohm resistor in there. Who is that? Is that Quincy? Who just said
Yes.
that? They put.
Me and Tape. I don't know who Tape is though.
Was that Tape? Are you there,
Yeah.
Tape?
Michael Tape. There's 2 Michaels, so I just started calling myself Tape.
Okay, but that must be Quincy, because one of you guys sound like you're from the country or something, and that was Quincy. Quincy, you the Quincy I know?
Yeah, Quincy from last semester. Yes, sir.
Oh, one of y'all guys sound like you're from down south. I'm trying to get the voice right. All right, anyway, that's not important right now. It'll be important when I see you guys. So you're right. So here's what they said. Here's the reason. What I'm not showing here that should be clear is I actually know the voltage drop across that resistor, don't I? What is the voltage drop across R? How many volts does it need to drop?
3 volts.
3 volts. 12 over here, 9 over here. The voltage drop across this resistor is going to be 3 volts. I'm actually using orange for voltage drop. So I'm going to have 3 volts across this resistor if it's the right size. Now remember, to get resistance, Ohm's law says that resistance equals voltage divided by current. But look at what I know. I know that for this to happen, for this circuit to work properly, that voltage drop needs to be 3 volts. So I can take this away and say, all right, that's going to be 3 volts. I also know that I have a series circuit. And what do we say about current in the series circuit? What do we know about current?
It's the same.
It's the same. So if this radio is going to have 200 milliamps flowing through it, that 200 milliamps has got to flow through that resistor. So I know the current in the circuit is going to be 200 milliamps. I'm going to write that as 0.2 amps. And so if I do my math here, I'm going to end up with 15 ohms. So whoever said that, you are 100% correct. 15 ohms. So you can go to the store, get yourself a 12-volt battery, a 15 ohm resistor, and you hook it up to this radio that requires 9 volts and 200 milliamps, then it'll work just fine because this will drop the voltage down from 12 to 9, and that's a safe level. But however, there's one more thing kind of implicit to this problem. You might not think about it, but what else do we need to concern ourselves with here? Power. So when they said, what size resistor do I need to put in series with the radio to get it to operate, the circuit to operate properly, kind of implicit in that, most people think ohmic value, and you would be correct. You got to get the ohmic value correct. But let me show you something about resistors that you would have learned tonight, but since we didn't meet, you didn't get a chance to learn it tonight. When you have a resistor, I can have a 15 ohm resistor like this. I can have a 15 ohm resistor like this. I can have a 15 ohm resistor like this. In other words, they make really tiny 15 ohm resistors, and they make really huge 15 ohm resistors. What do you think the difference is? If they're all 15 ohms, other than the physical size, what do you think the difference is between one and the other? What do you think it is? The bigger the resistor, the more what?
Power.
Right. The bigger the resistor, the more power. When we say power, what you mean is the more power it can what? Dissipate. Remember, when current flows through a resistor, the resistor takes that energy or some of that energy and changes it to heat. That's what we mean by power dissipation. And so when you hook this up, you'll get your voltage drop of 3 volts here, 9 over here, and the 9 and the 3 got to add up to 12. But also, when you put your hand on here, it's going to get warm. When you put your hand on here, the radio is going to get warm because it has resistance too. Anything that has resistance is going to dissipate power. The question is, if that resistor is too small, not ohmic wise, it's 15 ohms. I mean, as far as how many joules per second it can get rid of, that's what kills electrical devices. Most of the time, if you think about mechanical devices, something that moves over time is going to wear down. Electrical devices usually go, not all the time, but probably 99.9% of the time, heat destroys electrical devices. So you got to get rid of that heat. And so the reason this resistor can dissipate so much more than that one, the surface area is bigger. It can get rid of more joules per second of heat. Sometimes you'll have a small device and the size of the device can't be increased. The surface area can't be increased. So if I can't increase the surface area to get rid of more heat, they might know any other ways I might get rid of heat, where I don't have to increase the size of the device. What other ways are there?
Heat shields?
Heat shield. So a heat shield would be, if I have a metal case, I might take the resistor and actually bolt it to the side of the metal case. And now there's electrical conductivity. There's also thermal conductivity. If I have something, you know this because you ever take a pot of boiling water with a spoon in it, and you let the water boil, then you go over and you touch the spoon, you get burnt. It's thermal conductivity. So by taking the resistor against the metal case, it acts as a heat shield. It actually makes small heat shields you can connect directly to it. So yes, a heat shield is one way to do that. Anybody else think of another way that I can get the resistor, even though it's too small, I can get rid of a lot of joules per second, a lot of heat. What else can I do?
Airflow.
Airflow. Your PC works like that. In your desktop, they have a fan. I can blow air over it. I can blow air over it, and that'll get rid of heat. So if I can't make something bigger to increase the surface area, I can leave it small, but I got to have some kind of fan to take the heat away. So air is a fluid, and the fluid moves away, as it does through something called, in physics, convection. Heat is transferred from the thing we're talking about, in this case, the resistor, to the air and moved away from it. And another way, the final way to do it is moving an actual, like an antifreeze type of substance, another fluid, but you can actually pump liquids. Sometimes people with audio amplifiers, they have really expensive audio amplifiers where they actually have a special kind of antifreeze. They pump into the amplifier to get rid of the heat. So some kind of way you got to get rid of the heat. The point I'm making, guys, is given a problem like this, if you're in a class, it's okay to say, all right, I need a 15 ohm resistor. But if you were actually going to build this, and you really want to build this to make this work, then you got to need a 15 ohm resistor, but it's got to be the correct ohmic size, have the correct ohmic value, but you got to have the correct wattage too. And resistors are rated by the size, and I'll give you all of this in lab. But the bigger the resistor, you'll be able to look at a resistor and say, hey, that's a 1/4 watt resistor, or that's a 1/2 watt resistor. So you'll have all of that. But the point is, make sure you understand the concept. Anybody have any questions or comments for me over this problem? Problem number 1.
So
All right.
for this problem, the smaller one is the best.
No. Oh, you mean here or here?
Yeah, which one is the best for this
That's a good
one?
point. I didn't finish. Thank you. I actually didn't finish the problem, did I?
Yeah.
We got to figure out. Okay, which resistor do I use? What's the minimum wattage rating of the resistor? So I was about to move on and not solve the problem. So let's do that. So how do I find the power rating of that resistor? What do you think you do to find the power rating of that resistor? What is power? How do I calculate power? P is equal to what?
P equal to P squared by R.
I can use V squared over R. I can use I squared times R. I like to use this one, V times I. You can use any one you want, though. They should all give you the same answer. The question is, which V do I use? Do I use this V, do I use that V, or do I use that V? If I want to know the power dissipation of the resistor, which V do I use? Do I use one of the voltage drops, or do I use the voltage source? What do I use?
Voltage drop.
Which one? The 3 volt. The 3 volts. If I use 3 volts, I'm finding the power dissipation of the resistor. If I use the 9 volts, I'm finding the power dissipation of the radio. If I use the 12 volts, I'm finding the power dissipation of the whole circuit. I want to know the power dissipation of that resistor, so I'll use the voltage drop across that resistor times the current through that resistor. That resistor has 3 volts across it. And that resistor has 200 milliamps through it, which is 0.2 amps. Or that's 600 milliwatts or 0.6 watts. So that resistor, the power of that resistor needs to be greater than 0.6 watts. So would a 1/2 watt resistor work here? Can I use a 1/2 watt resistor?
Not without having an external heat
No.
sink.
Yeah. Now, without if I had a heat sink or a fan, I probably could, but I don't have that. So no, I can't use it. It's got to be greater than 0.6 watts. Now, somebody asked a good question. I'm not gonna ever get your name. Let me see. Hen.
Ne. Yes, I.
How do I say it? Is it Hen?
Ne. Ne.
Yeah, your name.
Yeah, my name is called pronounced like Ne.
Nin?
Yes. Ne.
Nin. Okay.
Yeah.
I don't know how
Yeah.
I'm gonna remember that. All right. Well, when I meet you, I'll try more. I'll remember it. But what
Yeah.
Nin said, she said, well, which one is best? Well, put it like this. I can make it too small, but I can't make it too big. So I can't go any less than this. But if I want to get a 100 watt, I can use a 100 watt resistor. I can use a 1 watt resistor, but I can't use a 0.5 watt. That's too small. I can use a 1 watt, 100 watt. I can use a 1,000 watt. It can't be too small. But now, of course, it wouldn't make sense to use this, would it? Why not? Because number one, it's going to be physically bigger. That probably won't work. And it's going to cost more. So typically what you want to do, it depends on the designer. If you're designing this circuit, what I would do personally is I'll probably just double this. I say, oh, I need at least 1.2 watts. No, but if you got a 1 watt resistor, would be just fine. A 1 watt would fine, but you can double it. It's kind of a rule of thumb. As long as you're greater than this. Now, let's say they made a resistor exactly 0.6 watts. Let's say you can go to the store and you can buy a 0.6 watt resistor. Would you want to do that to save money? Would that be the right thing to do?
No,
No, why not?
because you're really playing your margins there.
Exactly right. You're playing your margin in the sense that, number one, you're not going to find a resistance that is exactly 0.6 watts. It's going to be 0.6 watts plus or minus some error, number one. Number two, and you guys don't know this yet, but you will, resistance changes with temperature. Resistance changes with temperature. There's something called temperature coefficient. I'll get into that when you guys meet. But some things that when the resistance goes up, I've said that wrong. Some things that when the temperature goes up, the resistance goes up. When the temperature goes down, the resistance goes. That's called the temperature coefficient. So it could be possible that this change, and when this thing heats up, the resistance changes and take you a little bit below what that should be, and then you burn up anyway. So you don't want to be right at 0.6 watts. As a rule of thumb, just double it. 1.2 watts if they make the resistor. If they don't, come down to 1 watt. You definitely can buy a 1 watt resistor. These are standard sizes. And then use that in your design and you're good to go. No problem. So I don't want to, we beat this to death, guys. I'm gonna put the other two problems up just for a couple more minutes. You should have had time to do them, but I want to get those done and then let's take a break. So let me put these other two problems up for about 2 or 3 more minutes. Have you look at these again. We'll do those problems and then I don't want to get out of here. We'll do those problems and then we will take our break. We need to get a break in here. So here's a sheet. So look at number 2 and 3. Then we'll do number 2. Ooh, I love that tape. I love that. Your beer example, I'm gonna steal that. I'm taking that tape. You guys understand beerology. Beerology 101.
Sure, it's yours.
All right, so problem number 2. You got a 12 ohm and an 18 ohm resistor. They're in series. The current flow through the 18 ohm resistor is 150 milliamps. They want to know how much voltage exists across both resistors, and then they want you to apply Kirchhoff's voltage law to the circuit. That'll help you find the total voltage. So how much voltage exists across both resistors? So let's see what we can come up with. So here's the circuit I came up with. What we know is we got a 12 ohm, 18 ohm, they're in series. We know the current in this resistor is 150. We do not know the voltage. We want to know the voltage across both resistors. So how do I handle something like this? What do I do?
Find the voltage drop across each resistor.
Yep. I got to find the voltage drop across each resistor, but the problem is, it's not really a problem. In order to find the voltage drop across a resistor, to find the voltage drop, I got to know current, and I got to know resistance. That gets me the voltage drop. Well, they gave me this. One of them is 12, one is 18. But what do I know about current in the series circuit? What do I know?
Current is the same.
It's the same everywhere. So when they gave me the current in the 18 ohm, they actually gave me the current through the 12 ohm and everywhere else in the circuit. So it's really simple. I just use this formula on each resistor, and I'm good to go. So this voltage drop is going to be I times 12 ohms, and this voltage drop is going to be I times 18 ohms. And they told me what I was. I is, what was it, 150 amps is 0.15 amps times 12 ohms. And this will be 0.15 amps times 18 ohms. So if you have a calculator, I don't have one, but if you have one, what is 0.15 times 12? How much is that?
1.8.
This is 1.8 volts. So the voltage drop across the 12 ohm is 1.8. What about the 18 ohm?
It's 2.7.
2.7. I add that up, I get 4.5. So now I know that this thing right here, my Kirchhoff's voltage law, that source voltage is 4.5 volts. Question over that? All right, and then we'll put this one up, one more for about 1 or 2 minutes, and then we'll do that, and then we'll take our break. So go ahead and do that last one if you haven't already done it. If you did, just kind of hold on for a second, and we will talk about it. So number 3. All right, so number three resistors, 6 ohms, 12 ohms, and 24 ohms are connected in series across a DC source. The voltage drop across the 12 ohm resistor is 9 volts. They want to know what's the total voltage applied. So here's my diagram. I'm not showing the battery. You guys probably drew the battery over here, and that's fine. I wanted to show 2 circuits, so I left the batteries off. But just imagine the battery's there. The question is, what's the total voltage across the whole network? And I drew it twice because there's actually a couple ways you can do this. I thought I'd show you another way because these numbers are so nice. What do you notice about these numbers right here?
They're double.
Yep. I go from here to here, that's double. Here to here, it doubles. Now remember what we said about, if I write Ohm's law, V equals I times R, and I'm going to look at the relationship between V and R. So what I would do is I say that V, and I use this symbol right here, R, we call this is the sign of proportionality. This means that V is directly proportional to R. So since they're both, everything's in the numerator, I can write V is directly proportional to I, or V is directly proportional to R. In this case, I want to know the relationship between V and R, so I'm rolling it this way. Now, what does it mean to say V is directly proportional to R? What does that mean? Physically, what does it mean?
So when the resistor go up, the voltage will increase.
If I keep the current constant, if I increase this will go up. If I decrease this will go down. If I double this doubles. If I cut this in half, this is cut in half. So you can just use this relationship on this circuit to say, well, since when I go from 12 ohms to 24, since that's a doubling of resistors, if I double the resistance, I'm going to double the voltage drop. So then this voltage drop will increase from 9 to what? It will double to 18. And using the same logic, if I go from a resistance of 12 ohms to 6, I cut the resistance in half and going from 12 to 6, and I would just cut that voltage drop in half, and this would be 4.5. And then if you take a calculator, let's see, what's that, 27, is that 31.5? I did my math right, the total voltage would be 31.5. I think I did it right. And we didn't really have to do it. Is that right?
That's what I got.
Yes,
Yeah.
that's correct.
Okay,
I got
so
31.5.
we didn't really have to do anything there. If you understand this relationship, then that's not a problem at all. But let's just say you didn't know that. You didn't see that. And we had to figure it out another way. So then you say, well, I'm going to focus on the place in the circuit where I have the most information, which is right here. What I know about that 12 ohm resistance is I know, number one, the resistance is 12 ohms, and number two, I know the voltage across it is 9 volts. So what I can find a lot of things. I can find the power dissipation, but that's not going to help me. What I want to do is find the voltage drop across these other resistors, and in order to find a voltage drop, I got to have current, and I got to have resistance. Well, I know the R for each of these, so I already know that. The only thing I don't know in this equation is I. So if I find I can find all the voltage drops. So I'm going to use this relationship, these values, to find the current in the 12 ohm. Well, the current in the 12 ohm is going to equal the voltage across the 12 ohm divided by the value of the 12 ohm. Got 9 volts. And that 9 volts is across 12 ohms. Is that 0.75? That's 0.75. So that 0.75 is right here. But since this is a series circuit, whatever current is here is everywhere in the circuit. So I really know the current through every resistor. So if I take 0.75 amps times 6 ohms, we should get the 4.5 volts. And if I take the 0.75 amps times the 24 ohms, I should get the 18 volts. I'm not going to do what I did before, add them up, and I should find by Kirchhoff's voltage law, the total voltage is 31.5 volts. So a couple ways, and you'll find as we go on, guys, you'll find that there's always more than one way to solve a circuit. There's always more than one way. The more ways, the better. Anybody have any questions or comments about this problem? That's a pretty decent problem. I like this problem. So anyway, it's 8:20. Let's take a break for a few minutes, maybe 5-6 minutes. Take a break, and then we'll come back, and then I want to do some more practice problems. So let's take a break. I'm going to go off camera for a minute, and we will come back and do some more practice problems. Then I have a few more things to talk about, and then we'll call it a night. So see you in a couple minutes. There's about 60 more seconds, one more minute, and we'll start back up. If you're already starting, then you want to go ahead and work problem number 4. Problem number 4. So problem number 4, you have a 1,000 ohm resistor and a 3,000 ohm resistor in series. They give you the power dissipation of the whole circuit. They tell you it's 25 watts. They want you to find the voltage drop across the 1,000 ohm resistor. So see what you can do with that. All right, so here's my model of the circuit. Again, I'm not showing the voltage source, I'm just showing the main part of the circuit to solve the problem. We got a 1,000 ohm resistor in series with the 3,000 ohm resistor. It tells the total power dissipation of both resistors, and we want to figure out the voltage drop across the 1,000 ohm. Anybody come up with an answer? Somebody came up with, oh, so not yet. Michael says not yet. Okay, I'll give you more time. Take a little more time on this and think about it. Now we'll give you one hint if you didn't solve it already. There's several things you can go after here to help you solve the problem. There's always more than one way to do it. But what I usually try to do is find the current. And the reason I try to find the current when I have a series circuit is because the current is the same everywhere. So if I find the current, I know the current is both through the 1,000 and the 3,000. That may help you. It may not help you, but when I have a series circuit, I'm usually trying to find the current, and that tends to help me solve the whole circuit. But maybe you took a different approach. We'll see. Give you a couple more minutes. Ned says 79 volts. Okay. 79 volts. Niece, 79 volts. So we got a couple people saying 79 volts. We'll wait about another minute, and then we'll try it. We got an answer from two different people of 79 volts. So what I like to do is they gave me the total power. So they gave me a total, and I want to know a part of the total. Like I got the total power, I got the total resistance, I got the total current. Then I can have voltage drops across one resistor, the current in one. I want to deal with totals. I want to deal with parts. And since they gave me the total power, I want to use the total power because they gave it to me. They also gave me the total resistance. You might not think about it, but they actually gave me, I can add these up to get the total resistance. So if I work with total power and I work with total resistance, and I can also work with total current. So I know this and know this. I can find that if I have an equation that relates these three. Well, I do. I have 1 of Watt's law says P equals I squared times R. So by listing what you know and what you're looking for, I know this is 25 watts. I know this is 4,000 ohms. And I like to find current. Maybe you didn't find current. Maybe you chose to find voltage. You can do it that way too. You can find voltage and then use that voltage to find that voltage drop right there. I'm going to find current because in the series circuit, I just think that's the best thing to do. So I chose to find current. Your list might look like this though. You might chose to find the total voltage, and then you would use another equation, and you can work it that way. But I chose to find current. And since there's only one current in the series circuit, I don't have to subscript that as a total. There's only one. You don't have to subscript it as just one. So using that equation, total power equals current squared times total resistance. I can solve this for current, and then I can use that current to get my voltage drop. So if I solve this for current, if I do the math and solve it for current, I get I divide PT divide RT. If I divide both sides by RT, I get this. But then I still have I squared, divide this by RT and that by RT, left and right side. I gotta undo the square, which means I'm gonna take a square root. So when I solve that equation, I end up with that. Now, when you put that in your calculator, be careful, use your parentheses so that you take the square root the right way. But basically what you have here is total power. I got 75 watts divided by total resistance, 4,000 ohms. And I'm going to take that, divide it, so parentheses will force you to divide that in your calculator, and then take the square root of that. So whatever that is your answer. And I do believe, how much is that? How much current is that?
0.079 and
0.079 amps, and that would be 79 milliamps. So I now know that there's 79 milliamps going in that circuit. I like to put a circle around voltages. I usually put a square around my current just to make it stand out. The question is, okay, well, how much voltage is across that resistor? Now it's really easy. That voltage drop is going to equal the current through the resistor times the value of the resistor. I got 79 milliamps. Now here's something that's handy, guys. When your current is in milliamps, it's easier to do the problem if you have the resistors in K. So 79 milliamps, I multiply by 1K ohm. The reason is, if you think about it, milli is 10 to the minus third. You multiply that by K, which is 10 to the third, and that's equal to 10 to the minus 3 plus 3, which is 10 to the 0, which is 1. So basically what they're saying is, if you have your current in milli, when your resistance in K, you can just come in here and cancel these out because they equal 1. You can say I just got 79 times 1, which is, somebody already correctly said it, 79 volts. So the voltage across that resistor is 79 volts, and at least 2 people got that answer correct, and I'm assuming that probably some other people got it correct also. So you guys did a good job. Anybody have a question or comment on this circuit? Now, if you had chosen, instead of I here, you could have solved for V, T, and then you would have had the voltage across the whole thing, and then you could have took that voltage, you could have took the total voltage divided by the 4,000, the total resistance, you could have got current that way, and then use that same equation. So there's always more than one way to solve these problems. Okay? All right, now this next problem is kind of a challenge problem. There's not a lot of students that get this one correct, so it's kind of a challenge problem to see if you get it correct. So I'm going to put the problem on the screen, let you think about it for a while, and then I'll turn back and I want to draw the circuit to make sure you understand the problem the correct way, and then I'll give you more time to solve it. So here's the last problem of this topic sheet. We're not done yet, but just of the topic sheet. Problem number 5. I'm not going to do 6, guys. You can do 6 yourself, or if you want to do 6, you can do it and ask about it later. But I'm not going to do 6. I'm only going to do number 5. We'll stop there, then we'll move to a couple other topics. So see what you can do with that. We'll give you about another minute, but I'm going to read the problem. It says you have a 1,000 ohm 1/4 watt resistor and a 1,500 ohm 1/8 watt resistor, and they're connected in series. What's the maximum voltage that can be applied to this circuit without exceeding the power rating of either resistor? So when I read that, what I get is a circuit that looks kind of like this. So I'm going to let you look at this and think about it a few more minutes, and then we'll talk about it. I'll give you about one more minute, then I want to talk about the problem. All right, so here is my model of the problem. We got two resistors in series, 1,000 ohm, one is 1,500 ohms. Now, a couple things you want to understand about this problem. First of all, the 1/4 watt and the 1/8 watt. What is that? What do those numbers represent?
Power dissipation?
Yeah.
Okay, so don't confuse that with the actual power dissipation of the resistor. What that is those are the power ratings. So this, in other words, for this resistor, this is P max. This would be P max. So that's the maximum power dissipation for this resistor. It can dissipate up to 1/4 watt. You go over that, you burn it up. This is the maximum power dissipation for this resistor. So we're not saying that the resistor is dissipating 1/4 watt. We're saying that the maximum power it can handle is 1/4 watt. You go above that, you fry the resistor. So the question is, now, the other thing I want to show you is, you know the symbol for a voltage source is this. But I can also draw this. Put an arrow through it right there. This means the voltage source is fixed. When you see an arrow through any electrical device, that means it's variable, which means you can change it. So this might be a voltage source of 12 volts. Then this one would be 0 to 12 volts. There's a knob that I can change it up or down. I can do the same thing with resistors. I can show you a resistor like this. That's a fixed resistor. But when you come to lab, when we have lab, I can show you a resistor like this. And that's a resistor whose value you can change. That's a variable resistor. So what I want to do is I want to use this symbol over here. I want to put the arrow through it like that, which means that I can turn the voltage all the way down to 0. So I'm going to turn the voltage to 0, set it to 0. And then what I'm going to do is I'm going to slowly turn the voltage up. As I turn the voltage up, I want to know how high can I make the voltage without damaging either resistor. And whatever that voltage is, that's my maximum voltage for the circuit. The question is, what is that value? What is the maximum voltage I can set this to and not damage either resistor? Now I'm going to kind of think out loud on how to solve this problem. But before I do that, did anybody get an answer? Do you think you have an answer?
I think so. Doesn't mean it's right.
What do you get for an answer?
I got 30.6 volts.
30.6 volts. Anybody else get an answer?
I got 29.5 volt.
How much?
29.5 volt.
29.5. Okay. Answers? Anybody else? No? Okay. Well, let me ask you this. Of the two resistors, if I started this voltage at 0 and I started to crank it up, which resistor do you think would go out first and why? Which one would burn up first?
The 1/8.
The 1/8. Now, some of you might look at that and you might say, well, I don't know, because this is 1,000 ohms and that's 1,500. But that has nothing to do with anything. How much heat the resistor can get rid of, how many joules per second it can get rid of, is determined by the size of the resistor. And this can only get rid of, remember, a watt is 1 joule every second. So if I convert this to decimal, that 1/4 watt is, what is it, 0.25 watts. And the 1/8 watt is 0.125 watts, if I convert that to watts. But what that means is that that resistor can get rid of 0.25 joules every second. And this one can get rid of 0.125 joules every second. So that one can't get rid of joules as quick as this one. So probably this is my, like the weakest link. This is the weakest link right here. This is the one that'll go first. You just can't get rid of joules per second fast enough. So we want to work with these numbers. Now, if I use this value right here, P max, the maximum power that this resistor can handle is an 8 watts. So I'm going to use that. I know P max is 1/8 watt which is 0.125 watts as a decimal. And then I'm going to say, I want to find, given power, I know the power, the max power, given the resistance, I know the resistance, I can either find voltage or current. And since this is a series circuit, I'm going to choose to find current. I don't have to, I can find voltage. I want to choose to find current. So here's the list right here, what I know and what I'm looking for. Here's the list. So given that equation, given this list, I need an equation to relate P, R, and I. Do I have one? Well, I do. I know that P equals I squared times R. So I know that formula. We've already used that once tonight. But since that's P max, since this is P max, I can use this equation to solve for I. But since this is P max, then this right here is going to be I max. That's going to be if that's P max, then this is going to be the maximum current I can allow to flow through that resistor without burning it up. If I use the maximum power to get the current, then that's going to be the maximum current. So all you got to do is solve this right here for I, and I'm good to go. So let me change color here, pen. So just like before, I'm going to take I max. It's going to be P max divided by R. Let's say R2. And I'm going to square root that. So that should do it. That'll give me my current. And then we can use that current and Kirchhoff's voltage law to get my V max. So let's go ahead and solve that. This will be, I don't really use this blue a lot. I'll use the blue tonight. This will be square root 0.125 divide R2, which is 1500. So give me a current for I max. What's that evaluate to?
Nine milliamps?
All right, approximately 9 milliamps. Now what that means is this can handle up to 9 milliamps. If you go above that, this will burn up. This one will be okay, but the weakest link is that one. So that's our limit. We cannot go above 9 milliamps. So now I want to allow my current to be 9 milliamps. And if that current is 9 milliamps, then I got to figure out the voltage drop across each of those resistors. But that's easy now because we know everything. So I got R1. So I want to find V1 and V2. It's going to be I times R1, I times R2. If I got 9 milliamps, remember if my current is in milli, I want to write my resistor in K. This will be 1 K ohm. And that way I can cancel that milli with the K. This will just be 9 volts. And then I got the same 9 milliamps. This is a series circuit. This time times 1.5 K. I don't know what that is. What is 9 times 1.5? How much is that?
13.5?
22.5? I think it's 22.5. Yep. So this can be as high as 22.5 volts, and both those resistors will be okay. If you go above that number, then that resistor right there is going to burn up. So, guys, this problem is a pretty interesting problem. You can actually work this a couple ways. So I won't say I challenge you, but you might want to, when you have some downtime, see if you can figure out another way to work this. Like we could have solved this in my list. I had P max I had R2. I could have found V2 and solved it that way. You gotta be careful if you do that, because if you find V2, that's not this V, it's just the voltage across this resistor. So you got a little work to do if you do it that way. But the point I'm making is there's a couple ways to solve every problem. So a good way to learn is to solve the problem one way and then try to solve it another way. And what you'll find is the more mathematical tools I give you, the more ways there is to solve these problems. And it gets to be kind of interesting. So that's it for this. Anybody have any comments or questions over this problem?
So how about finding the voltage directly from P1 R1, or is correct? No.
No, because if you find the voltage or current for this one, then you've already surpassed the amount of current that this can handle. You got to remember, this can only handle an eighth watt.
Yeah.
So if you find the current for this one, you find the current for power of a quarter watt, which is higher than that.
Mm-hmm.
This then would be too much current for that one to handle. So no, that wouldn't be you got to figure out which value to work with. So these are maximum values. You got to figure out which one do I want to work with. You want to work with the lesser of the two. This is I don't know if you know what I mean by this, but this is the weakest link right here. This is the weakest link.
Mm-hmm.
That's the one you want to work with. Okay, so you might have to think about that, but that's fine. I mean, we'll run into a lot of problems that you got to sleep on to kind of understand what's going on. Okay? Well, guys, we still got more stuff to talk about, so I'm going to end this. And let's go back to our topic sheet to just kind of look at it and see where we are with things. All right, so I'm looking at the top here, number 1. And what you expected to know from this chapter, chapter 5, resistors in series are additive. Current in the series circuit, there's just one current. The current is the same everywhere. Voltage in the series circuit, well, that's Kirchhoff's voltage law. Kirchhoff's voltage law. The sum of the voltage drops equal the total voltage. Application of Ohm's law to series circuit, well, that's kind of what we did with problems number 1, 2, and 3, the practice problems. And then we did power, number 4 and 5. Now it talks about here something called series aiding and series opposing voltage sources. We got to talk about that. We talked about Kirchhoff's voltage law. It mentions something called voltage dividers, voltage divider rule. We got to talk about that. And then power in the series circuit. Power is always additive. We already talked about that. So it looks like all we got to do to finish up this topic sheet is we got to talk about what is this? What is series aiding and series opposing sources? We got to talk about that, and then we got to do this. We got to talk about voltage dividers and the voltage divider rule. We kind of already talked about voltage divider. I showed you one of those, but I'll remind you. Now we actually have another topic sheet. We got this one, and then we have a special topic sheet on batteries. So once we get done here, we still have some more work to do. Not a whole lot, but we got a little bit more work to do. So don't sign off if you don't have to once we get done with this. So what I want to talk about next is I want to talk about series aiding and series opposing voltage sources. And then I want to talk about voltage dividers and the voltage divider rule. So let's deal with those two topics. Now, you probably all have at some point, maybe you had like a flashlight or some kind of device, flashlights usually, where because of the way the flashlight is made, it's like a tube. So it's like a long tube, and you unscrew the end, and you put the batteries in there and screw the cap back on, and now you got a flashlight. Well, what you're doing when you put those batteries in there, say the battery is like this, Then you got that little part, the little bump. Then you put another one in there in the flashlight. Let's just say it's 2 batteries. Now this is a 1.5 volt battery, and this is a 1.5 volt battery. What you've done is you've taken one of these, which is 1.5 volts. You've taken another one of these in that flashlight, which is also 1.5 volts. And when you touch them together like that, you connect this point to that point. And so now the total voltage between here and here, what would that total voltage be if I measured that?
Three volts.
3 volts. Why? Because it's this voltage plus this voltage. Well, that's what we mean by series 80. The voltages aid each other or they add up. So an example of series 80 voltage sources would be to take 2 or more voltage sources and hook them together so that the polarity might have like this. So I got a plus minus. Let me make the polarity a different color. I got a plus minus, and I hook it up to another battery. And the polarity, this minus and this plus are together. And if I do that, if I hook them up, if this is V1 and this is V2, then the total voltage is going to be V1 plus V2. This is called a series aiding connection of voltage sources. I don't have to do it that way though. If I wanted to, I can actually do this. I can take and turn them the same way like this. And now my polarity is I have a plus and a plus and a minus and a minus, or I can do it the other way. I can have the 2 minuses facing each other. And then I would have a minus and the 2 pluses on the outside like that. Now the way to think about this is, remember current, conventional current flows like this. It'll flow out of the positive terminal into the negative like that. Well, if I have it like this, that means this is pushing current this way, and this is pushing current that way. And this was the same way. I got current going the same direction. If I think about voltages though, instead of having this situation, let's say that this was, let's say that this top battery was 10 volts and the bottom battery was 3 volts. Well, over here, if this is 10 volts and this is 3 volts, if I measure from here to here, series 80, I'm going to get 13 volts. But over here, these are actually working against each other. So here I would have 10 minus 3 volts, which is 7. And I have the polarity of the 7 the same as the bigger polarity. So this would be, since 10 is the bigger polarity, and it would be positive on the bottom and negative on the top. And the same here, only the polarity would be worse, or reversed. So when I have a situation like this, instead of V1 plus V2, I got to do a subtraction. This is called series opposing. This is series opposing voltage sources. So I have series aiding, I add them up to get the total voltage, and series opposing, I subtract them to get the total voltage, and then the polarity of the after subtraction would be the polarity of the bigger voltage source. Now, having said that, 99 times out of 100, when we do this, what we want is this one. We connect voltage sources in series to increase voltage. I'll say that a second time. We connect voltage sources in series to increase voltage. There are applications where you want to do this, but they're so far and few in between, it's not even worth mentioning. So
Could you give an example as to why you would use series opposing? Just something simple.
I can, but you wouldn't understand it. There's I don't know. Maybe you would. Maybe you got a degree in electrical engineering. Maybe you would understand it. But in some applications, like the one I think about right off is when you guys, this is if you're EET. If you're electromechanical, then what I'm going to say is not true. But if you're EET or biomed, you'll take a course called electronics. And in electronics, you'll work with a device called an amplifier. Basically, amplifiers take power and it increases the power. Some amplifiers require both a positive and negative voltage. So normally, when you power something, some kind of electrical device, when you power something, you will have something like this. This is the symbol for an amplifier. It's just a triangle. So you have on your amplifier, you have an input and an output, and this is like where your audio goes. But they'll show these symbols, like you'll have a power here. Usually you have a positive wire here. We'll call that, I'll just call it plus V. When you take the actual course, they'll put it like that, VCC, but don't worry about that. So you'll have that, and then you'll have ground. You'll have that ground. Well, some kind of certain amplifiers where you would use a situation like this, you actually have a positive supply and a negative supply. So they will call this plus VCC, and this would be minus, usually VEE. And you don't know what these symbols mean, but so I guess what I'm getting at is in very few applications, you need both a positive and negative supply. And I don't mean a plus or minus polarity, because when I do it the other way, that ground right there was the return on your power supply. I mean, you actually need a plus polarity and a minus polarity. You need a minus power source. You can only get that when you have a situation like that. So actually, I've been doing this a long time, and using that kind of amplifier is the only time I've ever seen this used over here, the series opposing. This is more important when you have, you could kind of like not on purpose, you can have opposing sources. You got to know what the total voltage is. It's not like you would do that on purpose. Other than this amplifier over here I was trying to describe to you, this might happen, and it might be kind of an unintended consequence, and you still got to know how to handle the voltage across it. So again, I don't really see that much often at all, but the series aiding is what you'll see. I don't know if that helped you or not, but.
And then for that one, did you say it was VT equals V1 minus V2?
Yeah, you would subtract these, and it would be, let me make this a little neater. You would subtract these, and it would have the polarity of the bigger voltage source. So if I had it like this, or the other way where I had it like this, I like to make these a different color. I think it stands out a little bit better. So I have a plus, minus, plus, minus. So if I said that this one was let's use 12 volts and 3 volts. Because these are, when I say fighting against each other, remember that when we think of a battery using conventional current flow, current comes out of the positive side of the battery. So this is trying to send current this way, and this was trying to send current that way. So if I think about it in terms of current, you can see those currents fighting against each other. They're going to cancel out. But we like to think in terms of voltage. So I got 12 volts with a polarity like this, and I got 3 volts with a polarity like that. Now if I do it like this, where I have plus on the top, minus on the bottom, or both plus on the bottom and minus on the top, I would just add them up to get 15 plus minus. But since these polarities are reversed, well, this was positive and this was negative, this one's positive and that one's negative, they're reversed, and this would be 12 minus 3, which is 9 volts. I'm gonna have the polarity of the bigger voltage source, so it'll be like that. And I actually have these reversed, but hopefully you get the idea. You just subtract them, and whatever the bigger number is, you keep that polarity when you move it over to get your difference. And again, don't focus too much on that. Know what it is and know how to subtract them and get it. But you're going to do series aiding, because usually what you want to do, you might have a lot of these voltages are a standard value. For example, a car battery is a standard value of 12 volts. Now, a long time ago, you guys are probably, I don't even know if you're even born, but years ago, I had a business, me and a couple other guys. We installed car alarm systems, car audio. And during that time, they had these lowrider cars where they had these cars, you might have seen them jump up and down with hydraulics and all of that. I didn't do that, but I was the electrical guy on the team. And then I had another guy that welded and did all the hydraulics. But those were 24-volt systems. And if you know anything about automobiles, you know that an automobile is a 12-volt system. So how do you put 24-volt hydraulics in a 12-volt system car? Well, you can do this. If I have two 12-volt batteries in series, and they're series aiding, then I have 24 volts. So the point is that you're going to put voltage sources in series when you want to increase voltage. Can you decrease voltage? Yep, you can do this. But other than that amplifier right here, this amplifier, I've never seen it. This is called a differential amplifier, by the way. I've never seen that before. So for us in here, we connect, if I ask, why do we connect voltage sources in series? The answer is to increase the voltage. It doesn't do anything for current. It only increases the magnitude of the voltage. Any more questions over series aiding or series opposing? All right, well, the next thing I want to talk about, and we actually might take another little break before we do it, but we actually have a kind of a small lecture to go into on batteries tonight before we sign off. Let me show you one more thing, and then we'll take a short break, and then we'll come back. We'll finish up with batteries, and then there's an assignment you have to turn in to me, but it has to do with batteries. So I want to talk about that, and then we'll sign off. I've already showed you a voltage divider. Let me just remind you how that works. I can take a battery and some resistors in series. And depending on the value of these resistors, they're going to drop a certain amount of voltage. If these are all the same, that's R, and that's R, and that's R. Remember, I have a 1K, 1K, 1K. 10K, 10. I just got all three equal resistors. And let's say that this is 9 volts. If each resistor is equal, and I have 9 volts, then each one's going to drop 3 volts. This will drop 3, this will drop 3, and this will drop 3. But what I can do, because I know that this is going to drop 3 volts, this is going to drop 3 volts, and this is going to drop 3 volts. What I can do if I wanted to, I can actually connect a wire from here to here, and I can connect up to that and I have 3 volts to use. Or I can connect the wire to here. Or I can connect up to here and I have 3 volts. I connect to here, I have 6 volts. Or I can connect to here. Now I have 3 volts I can attach to, 6 volts I can attach to, 9 volts I can attach to. So what they'll do is they'll bring this out all the way out like this, and then they'll have a switch, a 3-position switch, where you can turn it, you can click this from here to here to here. This might be right here, position A, this might be position B, and this might be position C. So now I got a switch. I can click this from A to B to C, and this will be my output over here. So if I'm in position A, I get 9 volts out. In position B, I get 3 and 3, I get 6 volts out. Position C, I get 3 volts out. So if you have any kind of device, they used to make these little, I don't know what you call them, powered, there's a little bitty box you can plug into the wall. You can move a switch, you get different output voltages on it. You can do it just like this. This is called a voltage divider. The resistors divide the voltage up, and you can use those voltages to do something. Now, on this one, I use all equal resistors, so I got a third, a third, a third, a third. If I have 4 equal resistors, it'll be a 4 for 4 for 4. But there's no reason why the resistors have to be equal. They don't. I can have any resistor down here to get any voltage drop. The only thing that's true is when I add up those voltage drops, it can't be any higher than my total voltage. Kirchhoff's voltage law says the sum of the voltage drops equal the total voltage. So I can play with these resistor values to get any combination, but I can't go above my total. So that is called a voltage divider. Now don't worry about that too much, because that's something we'll talk about later on in the semester if we get to it at all. Actually, we do a voltage divider lab in here. What's more important though is something called the voltage divider rule. So I want to show you that, and that's a very, very handy formula that you will use, and I'll tell you why in just a second. So let me show you the voltage divider rule. Well, I'll derive it for you first, and then I'll show you why it's important. So this is the voltage divider rule. They abbreviate this VBR. So if you see that, that's what they mean. And let me just do this. I'm going to have a voltage divider here, 2 resistors. So I got that circuit. I'm going to call this resistor 1. I'm going to call this resistor X. So got resistor 1, and instead of calling that resistor 2, I call it resistor X. That X can be any value. Now, if I put a voltage across here, let's say I put a voltage from this point to this point. If I put a voltage across that circuit, that would be my total voltage. I measure from there to there, that's my total voltage. I call that VT. But if I just measure across this resistor, so I can put another little dotted line right here, I can measure across that resistor, and that voltage is just, remember, you name the voltage after the resistance. So this is Rx, the voltage across it, that voltage from there to there, if that's Rx, then we'll call this Vx. So I kind of set this circuit up. I got 2 resistors in series. I'm not showing the battery over here, but it's VT. And then I say, all right, if I measure across the whole thing, that's my total voltage. I'm measuring the total voltage across the total resistance. But that partial voltage, Vx, I'm measuring that across Rx. If you set it up like that, what you can do is you can use your ratio and proportions that you learned about in math. You can say, all right, I'm going to take the ratio. I'm going to take the ratio of Vx to Vt, and that should equal the ratio of what? You tell me how to finish this.
Rx over R1.
Rx over not R1, but R what?
RT.
RT. I should be able to take the part over the whole. If I take the partial voltage over the total voltage, that equals the related partial resistance over the total resistance. The only reason you can do that is because V equals I times R. Well, since resistance and voltage drop and resistance are proportional, then I can write this proportion like that. And so this is a valid proportion. But what you can do here is just solve this thing for Vx. So I got this, a ratio. A ratio is just a division. This is a ratio, and this is a ratio. A proportion in math is two ratios that are equal to each other. And so you will find that because V and I are proportional, I said that wrong, because V and R are proportional, the ratio of the partial voltage to the total voltage is the same as the ratio of the partial resistance to the total resistance. That's a proportion. I can solve this proportion for Vx by doing this. I can take this side, multiply by Vt, and take this side and multiply by Vt. And then when I do that, that goes away, and here's what I end up with. Here's what I'm actually after. On the left, I got Vx. And on the right, I got Rx over RT. That fraction times my total voltage. That's called the voltage divider rule. The voltage divider rule. So you want to write that down and remember it. So now the next question is, all right, I get that. I can follow the math. If you can't follow it right now, if you watch the video when you're not tired and you watch it enough and play around, you would get the math. It's not a big deal. The question is, okay, well, why is that so important? Let me show you why. It's a real simple thing that turns out to be important. Now, we talk about series circuits. And the thing about series circuits, if you know all the values, all series circuits are the same. They're solved the same way if you know all the values in the circuit. Now, I'm going to give you some homework where you know all the values. I'm going to give you some homework where you don't know all the values. So you'll know, you'll have some unknown values. But let's say you know all the values. If you know all the values in the series circuit, to solve it, the first thing you'll do is find RT. You'll find the total resistance. The second thing you'll do, you'll use RT to find IT. So you find RT, use that to find IT, and the third thing you'll do, you'll use IT to find voltage drops. So let's just say I have this. I got that. I got 9 volts. I got 3 ohms. I got 6 ohms. And I want to solve the circuit. So by solve the circuit, what I mean is I want to see the current, all the voltage drops, and if I really want to solve the circuit, I find the current, the voltage drops, the power dissipation, everything you can tell me. I don't really care about power. Let's just solve the circuit. So let's find those values over there. So go down that list, find the values, and then solve the circuit for me. I'll give you about a minute to do that. So if you're going to solve this, you would say, we'll find the total resistance. Well, it's a series circuit, so I'll add them up. So that right there is 9 ohms. Use that 9 ohms to find the current. Well, the current is going to be the total voltage over the total resistance. Total voltage is 9 volts. Total resistance from that step is 9 ohms. I got 1 amp of current. So I know there's 1 amp of current flowing in that circuit. And then I want to find the voltage drop. That's what I'm after. Well, then the voltage drop, let's say I want this voltage drop right here. The voltage drop is just going to be the current through the resistor times the value of the resistor. I got 1 amp through 6 ohms. I got 6 volts across that resistor. I'm done. Well, using the voltage divider rule, I can get to this value by just saying, all right, if this is Rx, that's the resistor I want to know the voltage across. I just take that resistor, divide by the total resistance in the circuit, and multiply that fraction by the total voltage, and I go right to this answer. So I want to know, take the resistor, I want to know the voltage across. I want to know the voltage across that, so that's 6. Divide that resistor by the total resistance. Well, 3 and 6 is 9, so that's 9. Multiply that fraction by the total voltage. The total voltage is 9. So that voltage is going to be 6 volts. So basically, with the voltage divider rule, you never have to do this second step. You go right to the third step. Now you might say to yourself, okay, well, what's the big deal? Well, it turns out, again, just like when somebody asked me, well, give me an example of the series opposing voltage source. And I said, all right, go to your electronics class. You'll see these dual polarity amplifiers where you got to have, the only way to get that with a DC source is using a series opposing voltage source. I'll go back to the electronics class. When you deal with those amplifiers and you're solving the amplifier circuit, sometimes it's hard to find the current in the circuit. Not impossible, but difficult. With the voltage divider rule, you never have to find the current. So it actually saves you time. Now, you really won't see it on this level. It's just kind of handy to know, and a lot of problems in your book will use it. But in higher classes, it's just sometimes it's too much of a pain to find the current. You can just skip right over that and go right to voltage. So just trust me on that. It's a really, 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 really handy thing to remember. So add that to your, you'll see me do it, especially later on in the semester. I'll use the heck out of the voltage divider rule. I'll probably have to remind you of it. So remember this formula. Voltage divider rule, VDR. All right, well, it's 9:36, and we still got one more topic to talk about. So I'm going to take another break for about 5 minutes. I need to just relax for a minute. And I got one more topic. We need to talk about batteries, and I want to give you the battery assignment. This assignment is going to count as a quiz grade. So I owe you guys homework for last chapter and this chapter, and now you got this battery assignment that you got to do and submit. It's going to count as a quiz grade. So we'll talk about that after break. So take about 5 minutes. We'll come back, and the next topic we'll talk about are batteries, and then we'll be done for the night. All right, guys, we'll start in about 1 minute. All right. So here is our final topic of the evening. I want to talk about batteries, and this actually is this is new stuff. I think I added this to the course last year, and I decided we always talked about briefly about batteries, just kind of series aiding and series opposing batteries. But I added this last year because a lot of devices now are becoming wireless. You guys may have wireless earphones, wireless. Just a lot of devices are becoming wireless, which means not only are you using a radio signal to connect, like wireless headphones, you can have wireless headphones where you don't need the audio wire, but also if it's wireless, it's going to have a power source that doesn't plug into the wall. It's going to have a battery. And so batteries are becoming more and more and more important. General Motors made an announcement last week that by 2000, I believe they said 2035, all of their fleet's going to be electric. They're going to go from combustion engine to electric motors to drive their cars. And again, a big part of that being successful is going to be improvement in battery technology. And so batteries are important. And so I want to talk a little bit about batteries in some detail. So the first thing is there's this term battery and cell, and I want you to know the difference between the two. And I've shown you a symbol for a voltage source. One is this. And the other one is this. And what I said was that
I think
you
your
can,
screen's off, Ron.
oh, sorry about that. Okay, so what I've shown you was a symbol for voltage source here and one here. And I told you you can use them interchangeably, and you can, among friends, you can use them, they're equal. But strictly speaking, the one on the left is a battery. And the one on the right is a cell. Now, what's the difference between a battery or cell? A cell is the smallest voltage producing unit you can have. It's a single voltage producing unit. A battery is a group of cells. So you can see it even looks like that. This battery looks like two of these together. If I cover that up, that's a cell and that's a cell. So a cell is an individual voltage producing unit, a thing that separates charge. So you know the AA battery that you go buy or the D battery you go buy? The D battery is like this. Like the Eveready. That's not really a battery, that's a cell. It's a single unit that has a positive polarity and a negative polarity. It separates charge. It's a cell. It doesn't become a battery. The word battery means group of. Group of. So in the military, you have a battery of men, a group of men. When you say a battery of cells, they just drop the word of. They call the battery a group of cells. So a battery is a group of cells. So this is a cell. If you take and put this in the flashlight, you got another cell in there. Now you have a battery of cells, or in that flashlight, you have a battery. Now, what about your car battery? It looks like one thing. It's one thing. It looks like, one voltage producing unit, and it has a plus terminal and a minus terminal. And they call it battery and not a cell. But actually, if you could look inside of there, what you will see are these 6 chambers. There's 6 chambers in here. If this is a lead acid battery, it'll be 1, 2, 3, 4, 5. There's 6 chambers in there. And each one would have these lead plates in there and acid. And each one of those is a cell. There's 1, 2, 3, 4, 5, 6 cells. And each cell in your car battery produces 2 volts. This produces 2 volts, 2 volts, 2 volts, 2 volts, 2 volts. I got 2 volts 6 times. That's 12 volts from the positive to the negative battery. So it is proper to call your car battery a battery and not a cell, because it has cells on the inside that you can't see. So a cell is a single voltage producing unit. The thing that people call batteries, a AA battery, AAA, those are cells. They're not batteries. They become batteries when you put them together, more than one. Then you have a group of cells, or a battery of cells. You can call it a battery at that point. Again, I'm being really picky, but that's what it means. So, any questions over number 1? Battery versus a cell. All right. Well, then you have these are both voltage sources. You have ideal voltage sources and practical voltage sources. What's that about? Well, most of the time when you're in college and you're learning about this stuff, you work with this, the ideal. If you do design work or you actually build something from scratch, then you're dealing with this. So you have to know how to go from this to this. Even though we learn this, how do things really behave in the real world? How they behave? Now, let me show you an ideal voltage source. When I say show you, the thinking behind an ideal voltage source. Let's say I have this circuit right here. Got a resistor right here. Got a certain voltage. And what I'm going to do is I want to measure the current flowing in the circuit. So I'm going to put a meter right here that measures current. It's called an ammeter. So A is for amps, and I'll draw it as a circle. And so now what will happen is current will flow from my battery, from my cell to my meter, and I'll get a reading. But over here, I have that arrow. Now, what does that arrow mean? When I put that on that resistor, what does it mean? What does that arrow indicate?
Varying.
We talked about it earlier. A variable resistor. I can turn the knob and I can change that. I can go from 0 in theory to infinity. I can change it to any value I want. Now I want you to think about what happens to that current when I do that. Think about what happens to that current if I have a fixed voltage source divided by a resistor whose value I can change. I'm asking what will happen to the current. Let's say I start the resistor out real high. So this value right here is real high. and I start to turn the resistor down, lower and lower and lower. If I start to turn the resistance down, as this gets lower and lower and lower, what's going to happen to this?
The current gets higher.
The current's going to get higher, right? I mean, anybody can see that. Now let me make a graph of the situation I just described to you. What we're saying in doing this, here's what we're saying. We're saying that I have a relationship between the current of the battery and the voltage of the battery, where no matter what the current is, the voltage is this. That's DC. No matter what I'm doing, I'm actually controlling the current coming from that battery, but the way I'm doing it is by changing the resistor value. And what I'm saying is, when I show a circuit like this, I can make this current, by adjusting this resistor, I can make that current as big as I want, and the voltage is going to stay constant. The voltage is not going to change. That's a representation of an ideal voltage source. Now, you might not understand it yet until I show you the practical voltage source. Then you'll understand why this can't happen. Let me show you a practical voltage source. Let me show you first what it looks like. I draw an ideal voltage source like this. The practical voltage source I spell? I'm so tired I can't spell practical, guys. I get really sleepy when it gets. But the practical voltage source looks like this. And then you say, so there is a practical voltage source. Now, the practical voltage source consists of two components. It consists of the voltage producing part of it. That's the part of the cell or battery that separates the charge. However that's done, and the battery is done through electrochemical action. And the generator is done electromechanically. Some kind of way we're separating plus and minus charge to create voltage. So that's what this represents. So that's the V part of it. And what do you think that is right there? What is that? Just guess. What do you think that is?
A resistor.
It is a resistor, but is that saying that if I peek inside of my battery, I'll find a resistor? Is that what that's saying? What is that resistor?
Is that the natural resistance?
The what?
Like the natural resistance of the battery?
I know what you're saying. I think you're right. So guys, don't do this right now, but later on, you all have meters. I'm assuming you all have a digital multimeter. When you get time, take your digital multimeter, turn it to ohms. From watching that video, you know how to do that. Turn it to ohms. Take the leads and grab the leads and squeeze it as tight as you can and measure the resistance. If you hold it in your hands and squeeze those leads and look at the resistance, you're measuring the resistance of what? You're measuring the resistance of your body, at least across here. That doesn't mean if you open up your chest, you'll see a little bitty resistor inside of you. You're measuring all the resistance of all the biological material between these 2 points. You can draw that as a resistor. Well, here the battery is made up of chemicals. If it's a car battery, there's lead plates in there. All that stuff has resistance. So you can lump all that resistance together into this symbol, and that's called the internal resistance of the battery. Internal resistance. But the thing about it is, even though it's not an actual physical resistor, it still is a resistance. And resistances do two things. Resistances cause heat. They heat up when current passes through resistance. It heats up. So when you use your car battery or any battery, the temperature of it goes up a little bit. And resistors also divide voltage. So let me show you. You'll understand this. Real batteries have an internal resistance, a really low internal resistance. So I want to do two circuit analysis problems, one this way with an ideal source and one with an actual voltage source. So let's do it. Let's use this one first. So let's say I want to solve this circuit. I have an ideal voltage source and a resistor. This is a 10 ohm resistor, and this is a 10 volt battery or cell, the voltage source. And I want to figure out how much current is flowing in this circuit. How much current? Well, if I have an ideal voltage source doesn't have any internal resistance. And so the way you're going to solve the problem, you're going to think, well, shoot, Singleton, that's easy. If I want to find the current is equal to voltage divided by resistance. The voltage is 10 volts. The resistance is 10 ohms. My current is going to be 1 amp. So this is getting 1 amp. I got 1 amp flowing in this circuit. And so I can find the voltage across this resistor right there. The voltage across the resistor is the current times the resistance. I got 1 amp flowing through 10 ohms. That's going to be 10 volts. I got 10 volts across that resistor right there. Bam, I got it. You ain't even got to do that, right? You can look at that and see that the 10 volts is across it. The problem is that's not really what happens. It doesn't happen that way. What we're ignoring is there's actually resistance in the battery itself and internal resistance. So now let's do the same problem using the actual or practical voltage source. Instead of having this, you might have something like this. Let's say our voltage source, we'll have a small internal resistance of 1 ohm. So all the stuff that makes up that battery inside, if you add up all the resistance of the chemicals, the plates, it adds up to 1 ohm. So then you would have to put this box around it to show that this isn't an individual resistor, it's actually part of the battery. You put this dotted line around it. Now, like I said, an internal resistance. You see what happened now? Before we thought that the current flow here was 1 amp and that this got 10 volts across it. Let's see what it really is if the internal resistance of my battery is 1 ohm. Now when I find the current, I do the same kind of thing. I say, all right, current in the circuit is going to be the voltage divided by the resistance, but the resistance is going to be the internal resistance of the battery plus the actual resistor I'm concerned about. So instead of 10 ohms down here, it's really 1 plus 10, which is 11. I'm going to have 10 volts over 11 ohms. The 10 ohm resistor that I hooked up and the 1 ohm that's inside the battery that I don't know about. So I'm really going to do, now somebody needs to do this for me. What's 10 divided by 11? How much is that?
.909 ampere. 909
Let's just do this. We'll just call it 0.9, all right? We'll just call it 0.91 if you want. But you see, it's going to be different. So now, instead of having 1 amp, I really have 0.91 amps. And so instead of getting 10 volts out here, I'm going to get V equals I times R, but I is 0.91 amps times R, which is 10 ohms. I'm really getting 9.1 volts. So I'm not getting the 10 because I have internal resistance. I'm going to lose some voltage. I'm losing 0.9 volts across that resistance in there before it ever comes out of the battery. I'm losing voltage inside of the battery. Now, you might think to yourself, well, shoot, you're only talking about 0.9, but what's the big deal? Well, here's the problem. Let's say I increase the current. If I increase the current, the more current I pull out of it, the more current I pull from the battery, the bigger the voltage drop is here, which means the less voltage I'm gonna get over here. You can really see it if I do this. What if I lower this? Remember when I lower resistance, the current goes up. If I lower resistance, the current goes up. What if I lower this resistance from 10 ohms down to 1 ohm? You see what's gonna happen now? I got 1 ohm in series with 1 ohm. I basically have this. I got a voltage divider where I have the internal resistance, R internal, which is 1 ohm. And I got the resistor I hooked up, which is 1 ohm. So I got 10 volts across here. I got 10 volts across there. Now this is going to get 5 volts, and that's going to get 5 volts. So instead of having 10 volts out here like I want, I only got 5 volts. So this is really affected by a heavy current draw. So the bottom line is this: as long as your current draw is small, you can assume you have an ideal voltage source. But when you start having large current draws from a battery, now you got to take the internal resistance into account, the resistance inside the battery, because you're going to lose voltage across that internal resistance, which means your voltage at the output of the battery is going to be reduced. Okay, questions over ideal. Now this actually, I added this to the course, but you actually talk about this in electronics, but the problem is if you're electromechanical or I forgot the other major, you won't take electronics. So you won't ever see this. So I wanted to show it to you here. And there's some math that goes along with this, and I'm not going over. You know, if you're electronics, you'll go into it, but if you're not electronics, at least you've seen this and you know it exists, and you can think about it. Okay, questions or comments? All right. Well, so we're done with this one. I'm going to erase these. We're done with this one. Done with this one. And that leaves battery ratings to talk about. So I want to finish up tonight talking about battery ratings, and I'll give you this assignment. Now, the one that everybody knows about, and I'm not going to talk about, is the voltage rating. And what you might not know, remember you have the cells that we talk about? Like you got a AAA and a AA. So you might have this one, might be a AA cell. You might have this one, which is a C cell. And then you got that one, which is the D cell. Well, this family of cells, does anybody know the voltage of a D, C, or AA?
One 1.5, I think.
0.5, 1.5, 1.5. These are all 1.5. And you might say to yourself, well, dang, so they're all they're all the same voltage. So why the different thicknesses? What's the difference between the two? Well, there's two differences. There's I left something off of here. I guess make that D. Okay, so each of these batteries have a maximum current capacity. And you can probably guess that the bigger the battery, the more current it can put out or source. We say it sources current. So, wait a minute, somebody's got their mic unmuted. Let me mute them. Okay, all right. So the bigger, as a rule of thumb, the fatter the battery, the more current you can get from the battery. So yeah, these are all AA, AAA, C, D, they're all 1.5 volts, but this has a greater current capacity. So if you have an application where you're designing a circuit and you're going to power it with batteries, you got to know your current how much current your circuit is going to draw. Then you can determine which one of these I'm going to use, because each one of these has a maximum current capacity. Now, the only thing that's stamped on the battery is probably the voltage rating. This will be on the spec sheet of the battery. So if you're doing some other kind of design work, you could go to the internet, look up that battery, and there'll be a spec sheet for the battery, and you'd have all this information. So there's a max current capacity that the battery can put out, maximum current amount it can put out. So, but the voltage rating is, everybody knows, you may not know what it is. Most people know a car battery is 12 volts, right? So batteries have voltage ratings. I'm not going to say a whole lot about that. Now this one right here, the amp hour rating, you may or may not know about. By the way, I'm not going to talk about this one, because in this assignment that I'm going to give you tonight, you got to look that up yourself. You're going to do some research on that. So all I'm going to really talk about, I talk about max current capacity. I'm going to talk about amp hour rating. So the amp hour rating is kind of a number that they assign to a battery. And with that number, you can calculate the life of a battery. And it works like this. The life of a battery would equal, the way they write the equation, the rating called the amp hour rating, divided by the amps. So it's the amp hour rating over the current drawn, the amps drawn. That gives you the life of the battery. Now this is a theoretical equation. And I'll tell you what I mean by that in a second. So if I have an amp hour, say I have a battery rated at 100 amp hours, and I draw 2 amps of current from it. And ideally, I should be able to use that battery for 50 hours. So you can see why that's pretty valuable to know if you want to run something off a battery. Maybe you're going to send a robot to the moon. Of course, they have solar panels. They don't use batteries. They use solar. But if you were going to do some battery operation by remote, you want to know how long that battery is going to last. There you go. There's an equation. But it's a theoretical equation, and I'll show you why in just a second. Let me share some documents with you, and then I'll tell you why I'm saying that's a theoretical equation. So let me see here. These are some old batteries, but I like this because you can really see. So if you're looking at this, look at your, blow this up, zoom in on this, and what you'll see is several, you might recognize these. Look at this one. That's called a transistor battery, transistor radio battery. And if you look, I don't know if you can see this or not, but if you look right here at the bottom, they actually have the amp hour rating. It says, this is a milliamp hour rating. It says, I think it's 392 milliamp hours at 8 milliamps. And then look at this one over here, the flashlight battery. I can't read that number. Is that 4,000 or something? 4,000 or 4,500 at 100 milliamps. That ad is called a test current. And look at this. This is important because your assignment is based on this. This is an old car battery called a Delco DC12. But look right here at the amp hour rating. The amp hour rating of that Delco DC12 is 70 amp hours. And again, notice there's a test current. It's 70 amp hours at 3.5 amps. So all batteries have an amp hour rating. It might be a milliamp hour rating, but there's an amp hour rating on all batteries. Again, I've actually seen this stamped on the side of certain batteries. Like I was in AutoZone last year, and they had these small lawnmower batteries, and they actually had the amp hour rating stamped on it. So batteries have a maximum current rating, they have an amp hour rating, and they have a voltage rating. And with the amp hour rating, you can determine how long the battery will last if you know the current you're going to draw from the battery. That's the importance of the amp hour rating. Now, I mentioned that the amp hour rating this equation is a theoretical equation. I want to show you why. Now, this document I'm sharing with you is for this battery, that Delco DC12. And remember that Delco DC12, the amp hour rating was 70 amp hours at 3.5 amps. But these graphs are true for any battery. The numbers might be a little different, but the logic and the thinking is the same. So this equation is the one I just showed you on the board, that equation. And I said that it's a theoretical equation because amp hour rating actually depends on two things. It depends on temperature, and it depends on how much current you're pulling from the battery. That affects this equation. That affects the values you'll get for this equation. So let's look at, I guess the current draw is the easiest. So in this second graph over here, again, this is for the Delco DC12. Now remember, it was the Delco DC12, the amp hour rating was 70 amp hours at 3.5 amps. So if you look right here, on the bottom, they have current on this axis, and over here they have the amp hour capacity. And you'll see at that test current right here, 3.5 amps, the amp hour rating is actually 70 like it's supposed to be. But what happens as you draw more current? For example, what happens instead of drawing 3.5 amps or less? What happens if you draw 25 amps? How much would your amp hour rating be if you're drawing 25 amps according to that second graph?
55 amp an hour.
Right here. 55, about right in there. So what that's saying is, in this equation right here, where you would have, ideally, you would write 70 amp hours for that battery. Well, that depends on how much current you're drawing. You can use a 70 if you're down here at 3.5 amps or less. If you're up here at 25 amps, if the circuit you're hooking up to that battery is drawing 25 amps, then you got to put in the top of that equation, you got to put like 55. So in other words, the amp hour rating will depreciate or decrease with current draw. The more current you draw, it lowers your amp hour rating. That's one reason I said this equation is theoretical. So amp hour rating depends on how much current you draw from the battery. And then on the other one over here, amp hour rating also depends on temperature. And again, this is for the Delco DC12 battery. Remember, it was 70 amp hours at a test current of 3.5. So what this diagram is saying is you got 100% capacity at what temperature? Well, if you go over here and go down, at 80 degrees, you're at 100% capacity. What do you mean by 100% capacity? What I mean is the amp hour rating of that battery is 70. You can use 100% of the 70 if you're at 80 degrees. So if you're going to use that number in this equation, you can put the 70 amp hours in there as long as you're at 80 degrees. But let's say the temperature, it was winter, and the temperature dropped from 80 all the way down to 30. Now what would I want to put in that equation if I was using that same battery at 30 degrees? Well, you come up here and you say, all right, well, now my percent capacity was reduced from 100 down to 80. It doesn't mean your amp hour rating is 80. It means it's 80% of the total. So I have to take the 70 amp hours, because that's the total amp hour rating for the Delco DC12, and I got to take 80% of that. I will multiply by 0.8, and that would be the new amp hour rating that I put in this equation right here. So the takeaway is amp hour rating depends on how much current you're pulling from the battery, the discharge rate, and amp hour rating depends on temperature. The more current you pull, that lowers your amp hour rating. The colder it is, that lowers your amp hour rating. Now, if I wanted to, I can give you a problem that involves both, where the temperature drop and you're pulling current. You have to use both graphs together. I'm not saying I'll do that, but it is possible. Okay, so now I only got like a couple minutes, so let me show you one more thing. And then Do I have it? Let me see. I may not have it, guys. There's all right. I guess I didn't upload it. There's a battery assignment, and I'll make sure you get it. I don't know if I have it on. I thought I had it on Blackboard, but there's a battery assignment. Let me get off camera. Get on camera. So there is a battery assignment where you guys got to use this equation and those graphs. I think it might be on Blackboard. I probably just didn't. I came in here. I had to go get her medicine. That's why I was late. She has to take these pills, and I had to go to the pharmacist to get it, and I kind of got off track. So I might have forgot to upload that battery assignment. I'm pretty sure it's on Blackboard though. I'll check though. I'll check tonight or tomorrow. And then there's an assignment that you'll do. It should be self-explanatory from what I talked about tonight. One research will be this. I think the very first problem you research Cole-Frankingham's. They abbreviate that CCA, by the way. You'll see that. It stands for Cole-Frankingham's. And that's specific to car batteries or batteries that are used to control or work with combustion engines. That's CCA. So you'll do research on that. But then you'll answer some questions that's based on this equation and the formulas. So I believe that's on Blackboard already. You can check it out. If it isn't, I'll make sure it gets up there. So guys, I got like 1 minute. Does anybody have any questions or comments for me?
The current drain is equal to the discharge, right?
Say it again.
What is the current drain?
The current drain is how much current you're pulling from the battery.
So it's the same as discharge current?
It is the same as discharge current. That's right.
Okay.
Yeah. So yeah, that's the same. And guys, if you have questions, you can also. You know what? I think most of you did that quiz one, but when I was grading the other day, some of you didn't do it. I don't know why, because all you had to do was write down. I want to know what grade you're gonna get in the course and what you're gonna do to make sure you got that grade. And I actually had people that didn't complete that. Maybe I don't know if it was your class or the other. If you didn't do quiz one, you guys just kind of got to watch Blackboard to see. I'm going to see if we can do this lab next week, but just watch Blackboard to see if we're going to meet face to face or if we're going to do a lab. We need to get this lab out the way. But if you didn't do quiz one, I'll let you turn it in late. I don't take late work, but that quiz was meant to help you. And some people got zeros on it because you didn't bother to do it. So if you didn't do it,
I didn't do it. I thought it was due tonight. That was my mistake.
No, that's fine. Just do it and hand me the hard copy when you come in. The thing is some of those links that you turn into Blackboard, they're time stamps, and what happened, they'll disappear on you. Now people say, well, I don't remember seeing the link. Yeah, well, it disappeared. So if you didn't do that, I don't want you to have a zero for it. Just when we meet, and I'm thinking it's going to be next time. Hopefully the weather will work with us. Just bring that in, and I'll give you credit for it. I want everybody to get a good grade on that one. So guys, look, I'm sorry, I'm so tired. I'm out of gas. I got to get out of here. Let me see if you got any more questions, and then if you have anything else, we can talk by text. Anybody need any more questions tonight? Any questions, comments, concerns, thoughts, whatever? My day usually starts around 4 a.m. I get up, start taking care of my mom, and then my bedtime would be like 9 o'clock would be ideal, but I never get to bed at 9. So now it's like 10:30, and I'm just like really trying to push it here. So if you guys don't have questions, I'm going to go ahead and sign off. If you do, please send me a text, and if there's anything we need to talk about, I can always open up a link, and we can communicate through the camera. I don't mind doing that if we need to. But other than that, that's all I have. And you guys have a great week. And hopefully I get to see you next week. We'll see how it works out. And I'll see you later.
All right, Professor.
Thank you so much. Bye-bye.
Good night.
Thank you. Good night.
Thanks, Professor Ron.
Thank you.
See you Tuesday.
Bye-bye.